Hello, hello. Good Thursday. Almost the weekend.
Hello, everyone. How's it going?
Hello, everyone. Just wait a couple more minutes before we get started. Uh, yeah. Cool. Any questions before we start? Just share my screen here. Metaflow released something new. It's a new way to reuse code and whatnot. So for the last couple of days, I've been trying to update the code that I wrote using this new feature because it, cuts down the amount of code and it makes it so much simpler. But yeah, it's a lot of retooling that I have to do there. Yeah.
Sorry, what's the new feature?
And the new feature is the ability to inject. Uh, I'm getting a lot of echo there. I think it's from you, Wally, if you don't mind muting. I'm just hearing myself. So the new feature is it's a way to use decorators to inject functionality that you need on different steps. So for example, if you've seen the code walkthrough, one of the things that I do is a bunch of my flows load the data set, right? So that's something that I have to do. And the way I do that right now is with multiple inheritance. So basically I have a mixin, and every flow that requires loading the data set inherits from this mixin. And then I have to call a function that's called load data set in order to load the data set. So now with the new decorator, number one, the multiple inheritance goes away. I don't need it anymore, which is very confusing and I don't like it. And number two, any function that requires the data set, I can just decorate it with an add data set. And that will internally, it will load the data set and will make it available to the flow, which is pretty cool. So same thing happens with the loggers. I have to configure my loggers every time I want to use them, because remember, in a flow, every step could be running on a different computer. So every time I want to use the logger on a different step, I have to load it. I have to write code to load it. And that pollutes all of my code because you get all of these get logger. It's just ugly. Now, just using a decorator, it's going to be available for anyone. So it's much better. But I obviously have to go back and repull all of my code and retest and do all that good stuff. So yeah.
Lovely.
Yeah, no, I love when they release features like this because it makes the code better. Yeah, and then I can just incorporate it in the cohort, and anyone that's using it can take advantage of it. Cool, awesome. All right, so today we're going to be talking about serving model predictions. So far, we've talked about, how do you start a project? How do you build your model? How do you evaluate your model? The big question is, how do you actually take advantage of these models? After you finish building a model, how do you run inference on this model? The word inference is usually the word that we use to talk about taking advantage of this model by serving predictions, right? So putting it out there. Some people call it deploying the model. That's the word that you will also hear. So I'm going to try to cover this today. I'm going to try to cover a bunch of different strategies that you can use to do this. But yeah, this hopefully is going to be fun. So obviously, you probably have heard the saying that a bunch of models, like 95% of the models, don't make it out of a Jupyter notebook or something like that, right? And what that is pointed out is so many models that people create and never use them. And in fact, one of the areas that I've helped the most different companies is that they hire me because they have a team that built a model, but they don't know how to take advantage of that model. So that team does not have the experience or the know-how of, okay, so here's the model, it's working, right? If I test it, it's 95% accurate or whatever. What do we do with this? Like, where do we put it? Like, how do we call it? How do we make it useful? Okay. So that's a big part of the stuff that I've done. Okay. So I want to show you here a few examples so you understand what this actually means. Okay, so a few strategies that you could use and an example of what this actually means. This right here is an inference pipeline, and I'm going to explain in a second what do I mean by an inference pipeline. An inference pipeline, or a simplified version of an inference pipeline that I built for the electrical company that serves my state, Florida. Okay, so this Florida Power Light, that's the company that serves most of Florida. And what they were doing is they had a drone program, so they were flying drones, and they wanted to fly drones after a storm to assess the damage. And the idea was for drones just to take pictures of poles, that the big poles that you see around the road, and take pictures of all of those components and determine if any of those components were damaged. Okay, and not only doing this, not only they wanted to do this after storms, but do this preemptively, like maybe fly the drones once a month or so. The idea is just to take get ahead of any of these components breaking so they can replace them. So bunch of different components go into the poles. Obviously, that's a whole rabbit hole. Think about 3 different components now: insulators, arresters, and transformers. Those are just 3 examples. And this is what that pipeline looked like, or a simplification of that pipeline looked like. Our application expected a picture coming from a drone of one of those electrical poles. And then the first thing that we ran was an object detection model. So that's the first model that we ran. And the idea of that object detection model was to isolate and identify any every individual component on that picture. So anytime that we saw a component there, it doesn't matter what type of component, but a component, we wanted to sort of like isolate it, like get like a small thumbnail with the component inside. Okay. So then from that point on, we run a multi-class classification model for each one of those components. So coming out of the object detection component, we had like all of the pictures of transformers and insulators and arresters that we identified. And now we wanted to classify them because the object detection model we did not trust. Usually when you run object detection will identify the objects and will tell you what the class of the objects are. We did not want to rely on that. So we just wanted to identify the objects and then had a multi-class classification model that was trained a little bit better, let that identify the type of component. So, let's say we get 16 components out of the object detection model. We wanted to just name each one of those 16 components using this multi-class classification model. So that's two models working together. And then from that point, what we did was we had some sort of router, and that router basically was a simple condition. And that router said, okay, so if it's a transformer, we are going to engage the quality control transformer model. So basically it's a model that understands what good looking transformers look like, or what working transformers look like, okay? And will detect, or it will identify, or it will flag any transformer that was faulty, okay? So that's sort of like the idea of this pipeline. The reason I call it a pipeline is because, as you can see, this is not just one machine learning model. It's a group of models working together and, organized like a pipeline where the output of one model becomes the input of the next model. And this is very common in production because building a single model that's capable of processing a picture and automatically identifying every faulty component is very, very, very hard. Sometimes impossible. So it's much better to break that problem down into smaller, easier to solve problems, and then sort of like stitching together all of these models that solve the problem. So far, does that make sense? Cool. Jean, what's up?
Yeah, out of curiosity, you mentioned quality checking the transformers and other components. What kind of models do you use for that? Because you mentioned recently the autoencoders and whatnot.
So out of curiosity, you mean the quality assurance for those? Those were based on autoencoders, yes. So the heart of them were autoencoders. Those were anomaly detection models. That's what we used. I do not remember the specifics. I think for one of those, we use an LSTM, a long-term, short-term memory model. Basically, the idea with that, it was same idea, just detecting when something was not the same as before, but I do not remember the specifics of that one or which component we use. We had way more components than what you see here in the picture. There are a bunch of other components, which is just pain in the neck to label all of those. But yeah, most of them were anomaly detection. That was the idea of most of them.
Okay, thank you.
Anything else about this so far? Clear? Okay, so the reason I think this is important, or the reason I want you to think about this, because one of the takeaways here is whenever you have a problem, don't think about solving that problem like in a one-shot type of thing. Like, oh, this is the thing that I want to solve. It's much better if you try to break that problem down into smaller, more manageable things that a model can solve. I think I've talked about this before, maybe in a different session, where for one of the models, we even had built like something simple, like detecting the type or the brand of a bag. You get a picture and you detect, oh, that's a Hermes bag, or that's a Cartier bag, or whatever it is. We had to build just that. Requires multiple models just working together. Like, for example, one model would detect if the bag is rotated or not. So we ran that model, detected whether the bag was rotated, set it straight if it was, and then take that answer to the next model and so forth, and so on and so forth. So breaking that problem into smaller pieces is usually easier for you to get to a solution. Now, when you're building all of this, one thing that you have to take into account every single time are trade-offs. And we talked about this yesterday, I think, in office hours. There are always trade-offs. And the engineer's job is to identify the trade-offs and to make the right trade-offs. So basically to pick what makes sense at any given point in time. Okay? Everyone wants faster models that are very good and that cost nothing. Everyone wants that. Cheap, good, fast. You cannot have all three of them. So something has to give. Okay? So I like to think about this the unattainable priority triangle. And you get here the three components. There are, qualities here, and then cost, and then speed. And the way you read this is like the arrows indicates. Like if you're willing to sacrifice quality, then you will get a cheap, fast, but low quality model. Okay? So if you're willing to cut down the quality, I don't want predictions that are that great. Well, then you can get smaller model that's going to be cheap, right, to run. Okay, probably very fast. If you're willing to sacrifice the cost, if you don't care about how much it's going to cost, then you can get good, fast, but expensive models. And if you're willing to sacrifice speed, then you will get good, cheap, slow model. You cannot get all three at the same time. So here is a question for anyone who wants to answer this. Imagine a self-driving system, okay? Like imagine a Tesla or Waymo. What do you think is more important for them? Is it the quality of the predictions, or is it the speed of those predictions? Which one do you think they have to prioritize? Quality or speed?
Hard to
Speed, probably.
Okay, so I get speed. Who wants to take
Well,
the quality side?
their behavior seems to indicate quality, but I think it's slow.
So I see Guillermo says speed with a threshold. What do you mean, Guillermo?
if you can assess more or less if it's not accurate, I don't care about the speed because I don't want to risk anything, but I prioritize speed, but with caution.
Okay. So what the way they do it is that they have a budget. Okay, so they have a budget of speed, and within that speed, they want to maximize quality, but they only have a budget of speed. They cannot go slower than specific number of milliseconds, obviously, but within that budget, they try to maximize quality. So people usually, like, this is the first time that nobody takes the side of quality. Some people usually say, well, the quality is the most important. You don't want the car to make mistakes. It's like quality does not matter if you're too slow to respond, right? You're gonna die, and then 5 minutes later, the model is gonna say, oh, you should have turned left. It like doesn't matter. You're dead, right? But speed also alone is not the most important factor, because you can produce very, very fast the wrong answer. You don't do anything with it. So you have to find that trade-off. You have to determine how long do I have to answer the best, to provide the best answer that I can possibly do. Same thing happens with ChatGPT today. Okay, so if you go to ChatGPT, for most questions, you don't have the patience to wait for an hour. I can tell you the model will probably provide a better answer if it had 1 hour to work, but people won't have the patience to wait for it. Like nobody will wait. So you have to find that balance. That is what the model router, the new model router in GPT-5 is trying to do, is trying to predict what is the right balance to answer this particular question. Like if you ask me, who's the president of the United States, you are expecting an answer right away. You shouldn't be thinking about this. There's nothing to think about, right? That's a Googleable fact. That's something that you can search. So just give me an answer immediately. But if you give me a complex math problem, I would rather have you wait longer in order to get the proper answer. So those are engineering challenges. That is our job, to assess and to try to pick the best solution. Okay. So when we're working with these systems, another two things that we're going to have to deal with are latency and throughput. Okay. I'm going to go very quick on this. This is not a concept of machine learning. Just happens to affect us, just like affects everyone else that is building products. So latency is the time it takes for an answer, for a query to go to the server and come back with an answer. That's it. So how long are we actually waiting for an answer? That's latency. Throughput is how many answers can we get in a given amount of time? How many questions can we answer in a given amount of time? They're related, but they're not the same. Okay, so for example, imagine that we send one request to the model. So the user sends one request to the model, and it takes 100 milliseconds to hit the application, to hit that server. Then the server takes 100 milliseconds to communicate with the model. The model takes 600 milliseconds to answer. Then 100 milliseconds back. That's just wiring, or the communication. And 100 milliseconds back to the client. And if you add all of that up, it tells us that it's 1 second total, 1,000 milliseconds, which is 1 second. So the latency of this system is 1 request per second. That's the latency, okay? Now, the throughput might be completely different. So let's say instead of sending just 1 request, we package together 10 requests and we send them to the server, okay? And it's going to take a little bit longer to get there. So now it's going to be 150 milliseconds to get to the application, 150 milliseconds to get to our model. The model is going to take longer to answer because now it has to answer 10 questions, not just 1. So it's going to take 1,400 milliseconds. Then it goes back, then it goes back. When you add all of those up, you get 2,000 milliseconds, okay? That's the total, which means that the throughput is 5 requests per second. So in 1 second, you can answer 5 questions, okay? So why are these important? Because every time you design a system, when you deploy a model, you need to take into account what is the latency, what is the throughput, how can I structure this system in a way that feels fast? I don't know if you guys have tried to use a large language model without streaming. Streaming is that when you type, when they start answering a question, you start seeing the answer as it looks like it's typing the answer. So try to use a model without streaming and you will hate it because it takes so long, because you cannot display the answer until it's done with the whole answer. So it takes so long. The model takes exactly the same, but streaming makes it feel a little bit faster. That's why usually people talk about time to first byte. That's like a TTF, time to first byte. And they talk about that because it's how long it takes to receive the first byte from the model. So anyway, here is an example, just so you guys know how this affects in real life. So I've talked before that we were building computer vision systems for this robot, the Spot robot from Boston Dynamics. And we deployed the robot at a factory, or one of the deployments that we did was deploying the robot at a factory within a warehouse. But these are massive warehouses, okay? Massive. This is Anheuser-Busch. When we built this model, Anheuser-Busch is behind all of the beer that you guys drink here in the States, okay? So they produce a lot of beer and a lot of soft drinks. So anyway, massive warehouse. They even have streets within the warehouse for forklifts, okay? So literally streets with traffic signal is just crazy. And this is all on their roof, like a massive warehouse. The problem is that people, when they're walking around inside the factory, inside the warehouse, they know how to respect these traffic signals. They know when a forklift is coming, and they know to stop and wait for it to pass before they cross one of those streets. But a robot does not know any of that. And the forklift, I don't know if you've noticed, but they have the cargo in front of the driver. The driver sees shit in front of him, okay? So he's driving, he does not see what he's going. He's just following a path most of the time, or sometimes. So we cannot expect the driver to see the robot crossing. Has to be the other way around. So we had to build this model that we call it look both ways. Very fancy name, okay? And the whole idea of the model was to, the robot would stop at an intersection and will look both ways. So the camera will look here, will process the feed to see if there was a forklift coming, okay? Now imagine our model is a little bit slow. Let's imagine that for a second. So you can imagine that our robot gets to a corner or to a crossing and it takes a picture, right? So it takes the pictures that it has to process. So it's not a picture, it's a video, but just imagine it's a picture. So it takes a picture and there is nothing in that picture. At that point in time, there is no forklift coming. And then we send that picture or that set of pictures to a model, the forklift detection model, okay? And that model is a high latency model. It takes a long time for that model to return an answer because we have a very fancy algorithm to detect forklifts, okay? And while the model is working, look who's showing up. There is a forklift. At the end of the process, the model says, you know what, there is nothing here. So let's tell the robot to just cross the street. And the robot tries to cross the street at this point in time. There is a forklift coming right there. You see what the problem is? That high latency there completely kills our solution, makes our solution non-stupid, basically. It does not work. So in this is one of the cases where speed matters a ton. So having the best prediction quality is not the most important thing. It's the combination of speed and quality what actually matters, okay? All right, so let me check. There's two questions here. Want to make sure I answer them before I move on. The first one is, was the rotation detection model conceived from the beginning or you added it after doing some error analysis and saw that? Yes, so it was an afterthought. Basically, we did not know we were going to need that. Most people tell you you don't need that because, of course, deep learning, just doing that augmentation, the models will be able to do that. And that is partly true. So yes, doing that augmentation, you can get your model to detect things that are rotated for the most part, but you can do better if you only show the model pictures that are straight and you remove that component, that rotation. So we built a rotation model and we got the results. We got much better results, but that came after. Second question is, in a pipeline, is the error calculated at each stage or only at the final output? And if trained separately, does early stage age? So that is an amazing question. The answer is both. And in fact, one of the things that you have to do, and I had a slide for that, like in a previous cohort, I got rid of it. But when you're testing a pipeline, an end-to-end pipeline, let's say an end-to-end pipeline goes through 5 different models, and at the end, you can compute how accurate your pipeline is. The question is, how can you improve that pipeline? And one of the things that you need to measure is you need to measure each individual model separately. So you understand which model is bringing down the whole pipeline or which model you should focus on. And the way you do that is you simulate that all of the, like you remove the mistakes from earlier steps, if that makes sense. So if I want to test step number 3 and how good step number 3 is, what I do is I simulate like every answer coming from step 2 is perfect. So assuming there are no mistakes from model 1 or model 2, assuming there are no mistakes there, what would be the output if model 3 was better? And by doing that consecutively for each one of the models, you can measure which of the models is the worst one in your pipeline. so you can focus on improving that model. But yeah, that's what I will do. Okay, cool. So this is why this thing is important. So let's see some of the strategies, the specific strategies for you to deploy models, starting with the most common one, which is dynamic serving. This is the one that most people think about when they're thinking about deploying a model. And the whole idea with dynamic serving is that you're going to be answering requests as they come. That's it. You deploy a model and the model acts like an API. That's what it is. It's an API that internally is just going to process the input and produce a prediction and send it back. Okay. And you know, the advantages of this is that you don't need any storage costs. You're going to see that in a second, why that is important. And a disadvantage that it's sort of like variable latency, meaning when you get a lot of requests, the model is going to be slower, or you're going to have to increase the hardware that you're using to serve these predictions, obviously. So here is that example. This is very simple. This is very stupid. You have the user sends a request to a model, and the model produces a response. Okay, so think about this like ChatGPT. Okay, ChatGPT does not pre-store answers. It's waiting for you to ask. You know, the president of India. Yeah, that's what you do. And at that point, ChatGPT computes the answer to that and sends it back to you. Okay, so high computational costs for dynamic serving. Okay, so imagine that you're working for company Acme Inc. and want to deploy your model. You have to have a server running all the time. Okay, there's going to be a computer that's going to be up and running, waiting for people to send requests. Okay, and obviously it will require more complexity because you have to ensure scalability and availability. What I mean by that is your server cannot be down because it's not going to be available, and people are going to send requests and just going to fail. And number two, you need to scale. Like what happens if your application becomes popular, or if there is a sudden spike for some reason and people start using your model? One computer might just blow up and not be able to serve everyone. So these are concerns with dynamic serving. And that brings us to static serving, okay, which is a little bit different. But here, the idea is that you are going to pre-compute predictions and save them in a cache. So when people ask you to do something, you're not going to be computing anything. You're just going to be retrieving from that cache, from that storage, and giving it to people, okay? Obviously, static caching only works for low cardinality problems. So that means problems where the number of combinations, the options are low, okay? That is what that's what static serving or the type of problem static serving works on. So here is what that would look like. When somebody sends a request, the model, the application is actually returning the sample, the answer from a cache. It's not computing anything because it was pre-computed already. That model is running in the background, maybe every night, maybe, every day, is running pre-computing those answers and sending them back. So let me give you an example of a model that works like this. Is your Netflix homepage. When you log into Netflix and you get the homepage that says top 10 movies and the most watched movies in your area, none of that is being generated on the fly. All of that is pre-generated for you. Okay, so Netflix will run their models once a day or maybe 2 times a day to pre-generate that homepage. And then everyone in your area will just use that cached version for the homepage. Okay, you're not generating them on the fly. So static serving requires upfront computational load. That means that at some point you have to run those models. So that's going to be all of the computational power. It does not depend on user requests. It's sort of like fixed, but you have to go through it. You might be going through a lot of, compute without needing it because later nobody asks for anything, but you're spending it anyway. So that's sort of like the bummer here. And obviously it relies on pre-generated predictions. So the system is going to be less responsive to change. What that means is that a new movie might come out the last minute, and Netflix is not going to be able to incorporate that new movie in your homepage. Okay. Of course, there are tricks, and Netflix is a bad example for this, but you get the idea. You cannot react as fast as a model that's using information in real time because you are serving pre-generated predictions. Okay. So most people, what do? They use hybrid systems. Okay. So when you're building something, you might find an opportunity to combine both of these and use dynamic serving for high cardinality problems and use static serving for low cardinality problems, to combine both here. So let me show you here the way we built the or part of the pricing model for the bags. This is just part of it. But imagine that somebody's bags and watches and luxury items. Somebody sends a picture of a watch to our application, and we had to send it first to a model. This was in parallel, not necessarily first and second, but model one would identify the brand of that watch. So model one would say, oh, that's a Rolex, or that's a Casio, or that's a Seiko, whatever it was. Then the model two would check the watch condition. Okay, so model two would say, that looks like a beat up watch, or that looks like a pristine watch, or it looks in good condition. And then model three was statically served. Those model one and model two were dynamically served, meaning we could only engage them when we had a picture of a watch, but model three was not. So what we did overnight was, let's generate the combination of prices for every brand of watch and every condition possible. And by the way, it's way more complex than this. We did not do this using brands. We did use this using brand and model and year. So it's way more complex than this, but you get the idea. What we had overnight, we generated, okay, a Rolex in good condition, this is going to be the price. A Rolex in bad condition, this is going to be the price. A beat up Rolex, this is going to be the price. Let's go now to Omega and do the same thing. Let's go now to Casio and do the same thing. And all of those prices will be generated overnight and stored in cache in a database. And at the time of answering a request, we just pull out from the cache whatever combination we had, and that's the way we serve that prediction. Does that make sense? Here is a question. Uber. I want you to think about Uber. And one of the things that Uber wants to do is they would love to, when somebody picks a person, like, you have to go and pick up somebody, they will love to pre-generate the map, the route, before you actually ask for it, because it's going to be way faster if we know how to get from point A to point B really, really quick without having to generate that on demand. So what do you think? Can that be done using a static serving, or should that be done using dynamic serving? Who wants to give this a try? Kevin.
I guess I would say maybe it depends. Like for just any arbitrary route, it'd probably be difficult to do that. But maybe for like very popular routes, like from this hotel to the airport or something.
That is 100% correct, and that's how they do it. Mark?
Yeah, I was just gonna, probably not as good of an answer. I was gonna say, like, they might have like a baseline ETA and do some like additional changes on top of that baseline ETA for some of those like very common routes.
100%. But that's exactly, you guys, both of you have exactly the right idea. They cannot solve this for every single potential route combination because those are infinite. I mean, people can go anywhere. But there are specific areas in the city where they know that the action is, and most people live, like I'm thinking here, United States city, a lot of people live the suburbs. So they know there are specific routes over time that are most popular, the most popular, right? They could pre-compute the route from those areas. They could do that. And again, it could be millions, doesn't matter, but they could do that. And then, like Mark, like you said, they could adjust that on the fly. But now they are reducing the amount of compute that they have to go through during peak time. So peak time is there is a concert. When the concert ends, it's crazy. It's going to burn down Uber servers if they don't do this, okay? Because everyone is going to be requesting Ubers, and the servers are going to be computing over and over and over and over again the same route. So they could pre-compute those and then only make adjustments. And the rest, the obscure routes, they can just do on the fly. So it's a combination of static and dynamic serving. Mark.
So does that mean that they can combine both approaches for the same route, like saying, okay, we have some transition routes between suburbs or city centers, and the first mile and the last mile will be then dynamically
Well, what I mean is you will go not like that. So they will pre-compute the entire route, but that route might change based on that day's conditions, the road, the traffic, and all of that. So they could do readjustments as you're driving. You could be doing readjustments if necessary, but you know the end to, like if you don't do any readjustments, you're gonna take a person from point A to point B. So that's not the thing. They're pre-computing that, but then they can readjust that depending on traffic conditions and whatnot. The point here is, how do you reduce the load on the servers during peak time? And the idea is you cannot just use dynamic serving. You cannot just use static serving. You need to find a way to combine them both so you can actually be faster. That's what this is about. Make sense? Cool. Mert, I hear you. You're talking about prompt catching. We're going to talk about catching towards the end of this session. So I'm going to get to your question. Talking about the sketch related to the hybrid system used for the watch case. I'm not sure that I understand how it works, but why not catch the Model 1 and Model 2 with a recurring catch update? Okay, so let's think about that. I think this is what you're talking about. The reason we cannot catch Model 1 and Model 2 is because the goal of Model 1 is to look at a picture and tell me what watch is in that picture. What is the brand of that watch? My watch is different to your watch. So there is nothing for me to catch there. I cannot catch a prediction without seeing the original picture, right? But I can catch the price that I'm going to offer for a Rolex that's in good condition. That's not going to vary based on the picture. Does that make sense? That's why I can catch Model 3 results. I cannot catch Model 1 and Model 2. Hopefully that makes sense, but tell me if it doesn't. Cool. Here is another strategy here that you will also find, and it's a two-phase prediction. And I would say everyone here have experienced this, right? So if you have one of those assistants, even in your phone, the assistants are usually designed in a two-phase prediction approach, where you have a small, cheap, less powerful model ready to answer you, and a more complex model, larger, more expensive model in the cloud that the small assistant will hand over questions when they are too difficult. Okay, so that's basically what happens. So when you say, hey, name of the assistant, I'm not gonna say it, you can ask basic questions to that assistant, and some of those questions will be answered directly, okay, right away, because they are easy. But as soon as you try to ask something more difficult, then the assistant is just going to take longer to answer, and the reason is because you're handing that over a cloud server. By the way, this is different with Siri. Siri does not work. It doesn't matter what you ask, easy or hard. It's just a piece of shit. It's not going to answer anything. But it applies to everyone else, okay? Every other assistant. I'm an Apple fan, by the way. I'm just bitter that Siri is so freaking bad. So here is a real example of what that looks like. Yeah, so it's the same robot. And one of the things that we were doing, I mentioned this before, was reading analog gauges, okay? And if anyone here wonders why analog gauges. We are in the 21st century. There are digital gauges. Don't get me started. Yeah, that's not the way the world works, unfortunately. So you have the robot, and the robot was reading analog gauges, and we had a two-phase prediction approach to do certain things. So, for example, we took a picture, and we engaged the simple, quote-unquote, model that was running on device, the on-device prediction service. And that on-device prediction service, something that on-device prediction service did was do the gauge reading model and to do basic anomaly detection on that gauge that we saw there. So here is the example. We took a picture of a gauge. We read that the gauge was at 120 PSI, and we determined very, very easily, is 120 what it's supposed to be at? Like, do we know what the minimum and maximum are? So maybe it's supposed to be at 90, but now it's at 120. The robot will raise an alarm right there, right? Because that tank was too much pressure, okay? But we could not do historical analysis, which is also very important. And that is when we engaged the cloud model, okay? So again, it's just part of the same package here, just a more powerful model. And that more powerful model will look at the historical readings of that particular gauge to detect things like, for example, yeah, 120 PSI is not a problem, but last week was 119, and the week before was 117, and the week before was 115. So there is a pattern here where the pressure is increasing over time. We want somebody to look at this, okay? But we could not do that on the robot. We had to do that on the cloud. That's where the two-phase prediction comes in. Mark.
I didn't get the example completely. Let me ask. So the cloud service would know if a value that is in the acceptable bound doesn't behave as it should over time. That's why you have the cloud service.
So the cloud had access to all past predictions done for that gauge.
Okay.
Those past predictions were either coming from the same robot or multiple robots. It did not matter. The cloud had the database, number one, and number two, the compute power to run more complex analysis on those images.
Okay.
The robot only had the power to run one image, and that was it, right? We were already stretching it at that point. So we could not run an analysis. Didn't make sense either to run an analysis at the robot level, especially when you have a fleet of robots. Like, one robot doesn't even have all of the information that's necessary. So that's why we push to the server, and we run the second part of the prediction on the server. Make sense?
Okay.
Cool. All right, so let's talk about the model gateway right now. So we already saw model serving. If you guys have any other questions about model serving and how do you serve those predictions, just ask them in the Q&A. Let's talk about the gateway. The gateway is a very, very common pattern here where you create a unified API and put all of your models behind that API. Okay, so it's going to look something like this. So remember that last session we talked about input guardrails and output guardrails. That's why I have them here. But imagine, you send a query, you do context construction, you go through the input guardrails, but instead of hitting directly a model, instead of communicating with the model API, with ChatGPT API, for example, or Gemini API, now you're going to be hitting a model gateway, okay? And the model gateway, one of the things that it's going to be doing internally is, for example, routing. That's what it's doing internally. You're not hitting directly the model, you're hitting an intermediate layer that will decide which model you should be accessing to, okay? So routing is this. It's probably, the name is probably self-explanatory. This is what GPT-5 is doing now. They have a router, not GPT-5, the model, but ChatGPT using GPT-5, I'm sorry. They have a router internally, and that router will decide when to send your request, okay? Model gateways are more than just routing. You can do all sort of things there. So here are a few examples of the things that you can do when you have a model gateway. Like number one, routing. Number two, observability. So that means that in my model gateway, now I can log everything that's going through it. I can log every request. I can log every response. I can log everything. I can keep traces of everything that's going on in this model gateway. I can also do catching. Somebody asked about prompt catching. Well, this could be a place where you do some catching. Okay? And basically, when somebody sends a request that you pre-cached, that you already know the answer for, like if somebody asks, who's the president? Well, I already have that cached. I don't need to hit the model anymore because I can just return that from my cache. And we're going to talk more about caching later. You can also do security. You can also do cost management. Cost management here, think about like now that you're using LLMs, you could change where or what model you engaged based on a budget, for example. You can set a budget for your application and say, I only want to spend $100 a month. This is just an example. And have that be part of the model gateway. And the query, every time I get a query, I'm going to engage the best potential model, but I'm going to be checking the cost. And as soon as I get closer to $100, I'm going to start degrading the request. Everyone does that. By the way, Cursor does that. Cloudcode does that. Everyone, like the coding tools, they do that. They will degrade your experience if you use them a lot. So you can do all of that as part of that gateway. And by the way, the gateway will also gate which model is going to answer one specific question. So if you have an application and you can determine that certain questions are simple and certain questions are more complex, you could decide, okay, this is a simple question. I'm going to route it to Gemini Flash because it's very cheap, very fast. Oh, this is a more complex question. I'm going to route it to GPT-5. It's more expensive, takes longer, but it provides better answers. You can do all of that as part of that model gateway. Okay? So use model gateways to improve the resilience of your system. You, as part of your model gateway, you can retry requests. For example, something fails, you can say, if I send this query to OpenAI and it fails, I'm going to send it to Gemini now. Maybe get a response back. Maybe OpenAI is down. Maybe the model just fails to answer. You can do all of that as part of a model gateway. Okay, this is a critical component to decouple your application from the actual models. If you're working at a company and you build your entire solution on top of OpenAI, and they get bought by Amazon, and Amazon says, I don't work with anyone from OpenAI, and you have a model gateway, you're like, doesn't matter, I flip a switch. Now we're using Llama 4, whatever. It's just a piece of prep model, whatever. And thanks to a model gateway, you are decoupling your app from that. You're not coupled to any specific model. You can use any model that you want. Drozd, go ahead.
Yes, Cal, could you elaborate this a little bit more about caching? Do we need implement some kind of fuzzy matching or lag for this? Because prompts to
Sorry, let me stop you there. I don't know if there is a lot of echo, but I cannot understand what you're telling me at all.
Okay.
By the way, if you don't figure out the microphone, just feel free to just type it in the Q&A and I'll answer it right away. Any other questions about this so far? No? All good? Okay, so let's talk about then one of my favorite areas. And Ross, as soon as you figure that out, I'll answer your question. One of my favorite areas when deploying models is doing it together with humans. And I think I might have mentioned this in session 1, but I feel this makes the conversation of getting a project with a company, getting a project approved so much easier. than if I were talking about replacing people or just any mambo jambo like that. And you're going to see in just a second why this makes the conversation so much easier. But it's not only because of social reasons, but also because of technical reasons. Building something with a human component makes your job extremely easier than if you try to do it all of you alone. You guys are going to laugh, but I have deployed systems without a model. So imagine this system here, this model component does not exist at all. Okay, it's just fake. It's nothing. There's nothing there. I'm going to argue that this system still works. Without a model, still works. So it doesn't matter what you're trying to do here. Okay, so imagine you're working for a company, and the company is sending you pictures of parts, and your model needs to detect whether that part is broken or not, whether you need to replace that part or not. Okay, I'm going to argue that you could deploy a system where this model piece here does not exist at all, and everything else is still going to work. User is going to send the picture, and this has constant construction here because it's thinking about large language model. Just forget about that for a second. User sends a picture to a box that doesn't do anything. The box says, I don't know, nothing, returns false, whatever. That response gets to a gate that checks the quality of that response. And because there is no response, then this gate is always going to route it for a human. So the human is going to be the one ultimately providing an answer. And obviously, some of you are going to be looking at this and saying, sure, but are you stupid or what? You're not solving the problem. No, I actually am. I'm creating a pipeline that eventually will start taking work off people's plate. People are going to be driving the results at the beginning, but for every little bit of work that I put into this model, they're going to be less and less work will go to humans. So I can start with just the pipeline and people keep reviewing everything manually. And then I start working on my model, and my model now is capable of solving 10% of the images, and now it's just 10% less that goes to people. And then 20%, and then 50%, and then 80%. And before you know it, people are doing less and less and less of the work. Does that make sense? Like the way to think about this. Do you guys understand that? This makes, technically speaking, is an amazing tool or trick for you to go out there and deploy, because you don't have to spend time here at the beginning. You're just spending time in the whole process. You're stitching together the entire process so it works and it can grow with you. Here is the beautiful part. Every time you send something to humans, they will have to provide an answer for that, whatever that is. Let's say it's still just to stick with images. And that answer is, or those answers are labels. That's ground truth that you can use to train a model. In fact, I'll argue that if you don't have any data when you're starting, you should not be waiting to collect that data to start. You should start building this and putting all of the pieces together and let the data collect itself, quote unquote. If I deploy this in production, data is going to start collecting itself. Because now we are going to start analyzing images and people are going to be providing labels for those images. Does this remind you of the watch application that we saw during session 1? It should, because it's the same idea. You put together a solution that is not using a model, but that solution is in production and is helping you label data. It's helping you collect data that you're going to use to build that model and to take some of that load off of people. Okay, so this is this model that you see here, this diagram that you see here, is like the pattern, the template. Gonna see how we can adjust that template a little bit. Go ahead, Mark.
If I get you right, that what you say here is what you said in the very first session. I think you say deploy an end-to-end pipeline and try with the easiest approach. And the easiest approach is not to change anything, but let the people do it because they already done it.
Yep.
Did I get you right there?
Yep, that's exactly it. Trust, I see your question. I'm going to talk about specific techniques for catching at the end of the session, so that will answer your question. Dinesh, by the way, Dinesh, I see your question here because it popped up on my screen. But anytime you want to answer, you want to get an answer, put the question in the Q&A because I'm not looking at the chat. It just happened to pop up, so I saw it. So I'm going to answer it. Do we need human-in-the-loop response back to live model version 1 or take the data and prepare model version 2? So yeah, so the answers from the human, they will go to a data set that we will later use to train the second version of the model. So the answer does not go to the model because the model doesn't do anything with that answer. We just need to collect that data so we can retrain a new version of the model. Okay, so that's what's going to happen. This is what I already mentioned. Obviously the human feedback is high quality training data. We're going to be training the second version. Think of it like this. This is what you should be thinking about, where, the model is going to send a response. I mean, the human in the loop is going to send the feedback that we're going to collect in the data set. And this data, we're going to be using it to train the new version of the model. And that's going to be the model. And, the whole process will start again. So it's just a loop. And every time we have enough training data, we're going to deploy a new version of the model that's going to be a little bit better than the previous one. That's basically the way it is. Leon.
Would you also add the functionality that even if the model could answer the question that you route it to the humans just to get more data going forward?
Yeah, so I'm going to show you that right now. So I show you this sort of like strategy here. The way I motivated it is by saying you don't even need a model to do this. But this can get a little bit more complex than that, okay? So let me see what I am. So I'm going to give you a couple more examples, and maybe this is going to answer your question. So the question is when to trigger. When should you trigger the human-in-the-loop connection? Like, when do we send this to a human? Okay, so at the beginning, if there is no model and I deploy that solution, well, obviously everything is going to go to the human, okay? But there are multiple ways to trigger hey, I need to involve a human here. Like whenever you're uncertain about an answer, for example. So how uncertain you are, that could trigger it. What is the confidence of the model on that particular answer? Imagine that you have a binary classifier. When you have a binary classifier or a multi-class classification model, one of the things that is going to come out of the model is how confident the model is on that answer. Well, for lower confident answers, maybe send it to a human. Or, specific scenarios. Oh, this is an image about this particular component. I don't want to touch that. So like in my case, for example, when I was building the bag thingy, we did not want to do a lot with Hermes bags because they're really, really expensive. So we did not want to, we want humans to take care of that, okay? There's too much money involved in Hermes bags. So here is an example. And this is a fairly sophisticated example. It looks pretty similar to the one that we saw before because it's the same idea. That's why it looks similar. The magic happens in how we send to humans, okay? So imagine this scenario. So the user sends the system sends an image. Let's say it's an image, okay? So the model tries to make a prediction on that image. It makes a prediction on that image, but we're not going to send that prediction directly to the user back. We're not going to do that. Instead, we are going to ask, has this model seen this image or an image like this before? That's the question that we are going to ask. How do we do that? Any idea? How, given an image, how could you possibly know whether the model has seen an image like that before? How would you implement that? Any ideas?
Similar to vector embeddings that we use. Maybe we can have image embedding.
You could use vector embeddings, right? So every time I get a new image, a new request, I could generate the embedding for that image and save it. Okay? And then later on, for any given image, I could go to my database and say, are there any images that are very, very similar to the one, have a threshold there, to the one that I just received? Now, why is this important? Why do you guys think I'm asking this question? Why would it be important to know whether the model has seen something before? Mark.
Which Mark? Fine. Okay. Because if the model has never seen such a picture, it's highly likely that it will wrongly predict whatever it should do with the picture. No data, unknown class, unknown cluster.
Yeah, I mean, if the model has never seen a picture like that before, something similar, why would I trust the model? I shouldn't. So that's one criteria. I'm going to say, if you have not seen a picture like this before, let's send it to the human. Okay? I'm not going to send the answer, the final prediction to the user. Let's make sure you mute yourself. There is a lot of audio coming in. So just make sure everyone, you mute yourself. So if I have not seen that image before, I'm just going to store the prediction, do all of that in the database, but I'm never going to show the human. I'm never going to show the user that. Instead, I'm going to send it to the human. But what happens if I have seen that prediction? What else can I do? Let's say, not the prediction, I'm sorry. Let's say the answer is, yes, you've seen this image before. What do I do now that I've seen that image before? Who wants to answer?
I didn't get your question.
Okay, so you know that if I have not seen that image, I'm not going to send the answer to the user. I'm going to involve a human. But what happens if I have seen the image? Stuart.
Would you check to see if you gave the right answer before for that image?
So if I've seen something like this, I can check, okay, did I answer it correctly before? Right? Like, did I get answers like this image correct? And if the answer is yes, then I will provide a prediction. If the answer is no, well, yeah, I might have seen images of a cat before, but I always get cats wrong, so I will not try to answer. Vishwana.
Right. But you mentioned if we haven't seen the image before, then we directly send it for the review. So if we already have the review, the next time that we send the response, isn't it already a reviewed answer?
You mean review? Is that the word that you're saying?
Yeah, in the diagram, you have that send for the review, right? So let's say if
Let's play it out. Let's play it out. I deploy this. Okay? Deploy this for the first time. Somebody sends me a cat picture. Model says, I think that is a cat. That's what the model says. But I get to this check, and the check looks in the database and says, you've never seen a cat before. So I know you're saying it's a cat, but this image of this animal here, you've never seen one before. So I'm not going to trust your answer. Okay? So I'm going to store this picture with an animal, answer from the model cat, and I'm going to send that to the human. The human is going to look at the picture and say, yeah, this is a cat. That answer is going to make it to the user. Second image is a cat. Goes to the model. The model says, yeah, I think that's a cat. We get to this check. The check says, oh, yeah, I see that that is a similar image to one that you saw before. And I see that before you got it correctly. Therefore, I'm going to trust your answer by now. And that second image then is going to make it to the user. Does that make sense?
Yeah, so is this, just an example. So yesterday we were using cosine similarity. So is it like some threshold like that? I mean, based on the
threshold, yes, you will have to set a threshold or how similar those images have to be. And again, here what you're protecting against are images that look completely different from anything that you've seen before. And you're also protecting against classes of images that you always get the wrong answer on those classes of images. You're just not good at them as a model. Make sense?
Right. Oh, thank you.
Remember, the key here is that you always generate an answer and you save that answer regardless of whether that answer is going to be used for the user, is going to be given to the user or not. But you always save that. Like you keep your work and we keep annotating all of that work in the database. So next time you go through, we know like how you've done here before. By the way, let's say it's a cat picture number 100, okay? And then I go to the check past performance and it says, yeah, you've seen 100 pictures like this before. And on average, you're 90% accurate on those pictures. So you're going to have a threshold there and say, well, as long as I'm above 90%, I'm going to trust the model because the model is really good. But then it's an elephant and the check performance says, yeah, you've seen 100 elephants before. And on average, you're 75% accurate. I'm like, no, shoot, I don't want 75%. I'm going to send it to the human. Does that make sense? That's the way the system works and adapts as it gets better. You're going to get better answers, okay? And the number of requests that are going to be directed to humans is going to fluctuate with the system. Hopefully, the next retraining window, we're going to incorporate all of that high-quality data from this data set that we have been collecting here. We're going to incorporate all of that to the training process. So our model now is going to be even better. Does that make sense?
Yes.
Okay. Something that makes this even a little bit more sophisticated. Okay. I've done this before. Super cool. And it's this is the type of thing that you sit down in a meeting with a company and you explain this to them and they are just giggling, and you're gonna see the company just doing like this, okay? Because they love this type of thing. So it's when you incorporate the costs, the potential costs of making a prediction into your system, and your system acts in a way that tries to reduce the costs, okay? And the whole idea here is just using cost sensitivity. We talked a little bit about that during session 2, I think. This is like an actual example of how you will use it. Again, same structure. What changes is how you evaluate. And here, the evaluation is basically using the potential cost of making a mistake to decide whether to involve a human or not. So let me give you just a specific case. Okay, this is a specific example. Okay. We are taking pictures of equipment and we want to determine whether a part is going to break. So we can do preemptive maintenance. Okay, so that's the whole idea. So I sit down with the company and I ask the company, okay, so tell me what happens if a component breaks, what happens? And they tell me, well, if a component breaks, the whole factory stops and we're going to lose $4,000. Okay, that's great. So tell me now what happens if a component is not going to break, but I mistakenly tell you that it's going to break. And they think about it and they say, okay, I have to send a maintenance crew and I probably have to order the part, but then I'm going to have to pay for storage for that part. Just a big mess. $1,000 of cost if you make that mistake. And I'm going to write those down. I'm going to say, okay, So if I make a positive detection of a component that is going to break, and it turns to be negative, so the cost is going to be $1,000. But if I miss that a part is about to break, a component is about to break, that's going to be a $4,000 cost. Obviously, getting it correctly, the cost is going to be 0. So I'm not going to have anything there. I'm just writing down the costs of making mistakes and sending it to a human. So the human evaluates that part. That's going to be a $200 cost. So obviously, we want to minimize the stuff that we want to send humans because humans are expensive as well. So with this information, now in a simple binary classifier, I can use this information to make better decisions. So what is that? What does that look like? So imagine that we have a model that needs to detect whether the part is about to break or not. And let's say it makes a prediction that the part is going to break with 60% confidence, okay? So the model is telling me, yes, that is going to break, and I'm 60% confident that that is what's going to happen. So I can simply compute using this matrix, I can simply compute using this formula, whether to send it to a human or not. The model is telling me it's about to break. So I'm going to say, if the model is making a mistake, this is the confidence that the model is going to make a mistake is 100% minus the 60% confidence times $1,000, because this is a positive case, but if it's actually negative, it's $1,000. That's going to have a potential cost of $400 for me. If I send it to a human, the cost will be $200. Therefore, whenever I get in this scenario, I'm always going to send it to a human, because it's going to cost me more to make a mistake than what I'm going to be paying for the human to review this. But let's say now the model answers, oh, that is not going to break with 98% accuracy. I can do the same thing, 1 minus 0.98 multiplied by $4,000, that will be a mistake. If I say negative and it's actually positive, the cost will be $4,000. So that will come out as $80. If I send it to a human, it's going to be more expensive. So I would rather take the chance and make a prediction here that says, nope, this is negative. So in this case, the decision will be make a direct prediction. Don't send it to a human. I mean, you don't have to understand the formula. We can talk about that later. But does this make sense? Here you are incorporating actual business costs into your prediction process in order to make better decisions. Mark.
A true positive hit will also create costs, right?
Yes.
Would we incorporate this also in the cost matrix? Because you go there with 0.
So the human cost, if that is what you ask, costs $200 to send it to a human. It's a fixed cost that we're just taking into account here.
Right, but what I want to say is, if you have a true positive hit, your company also has to do something, so there are also costs attached with that.
You could incorporate it here. It's the same thing. So yeah, not a lot is going to change because you will also have to incorporate.
Yeah, of course, but it's a small delta. If we go for the dollar, it might make sense to say, okay, and with the same model, you can look if it is worth ignoring the true positives.
So in this case, you ignore the true positives because it doesn't matter how much it costs. You have to do it anyway, right?
I see. Yeah, then it's 0.
Right. You have to replace that part. If the model says that you have to replace the part, and you do have to replace the part, sure, it's going to have a cost, but you have to do that. It doesn't matter how much it costs. You have to do it. The model cannot recommend not to replace a part because you have to do it. So in that case, cost is 0. It doesn't matter. Make sense? So go ahead, Mark.
I may have missed this, but for this type of like cost sensitive evaluation, Am I understanding right? Like you're not baking this directly in the model, like within a loss function or something like that, but you're taking the output of the model and like doing some bolt-on business rules.
That is correct. You could bake it into the model. I don't like to do that. I personally don't find that useful, especially because it's really, really hard to adjust. So if you
Makes
bake
sense.
it into the model, the only way to adjust that is retraining. That's the only way to adjust that. If you
Thanks.
do it outside of the model, it's very easy to manipulate. Something else on top of that is that the human cost here, that's what I told you before, that we could make it even a little bit more sophisticated. Here I have a human cost of $200, but in a place where you have a lot of requests, when this is not a one-off that you run every day, but you really get a lot of requests, the human cost will fluctuate and it will top off. Like you cannot involve infinite number of humans. So the cost, it does not scale. Like the $200 is just for one person, but what happens if I need 2 people? It's still the cost 200 maybe, but what happens if I need 100 people? Now it does not scale. So what you will do in those cases is you can have a simple function that modifies the cost of a human based on the number of tasks that were generated for humans. So you could imagine a system that at the beginning, when you start, the system starts flooding that queue for humans because the system is very concerned with making mistakes. So it's going to say, I'm not going to try to make too many decisions. Let the humans take care of that. But as the system adds more tasks, the cost of sending it to a human will increase automatically. And there's going to be a point where the system is going to say, you know what? I cannot send that many tasks anymore because now it's cheaper for me to try to make a decision. Because if I send it to a human, the cost is just too high to send it to a human. So you get this beautiful system that's going to auto-regulate by you modifying the cost of sending it to a human. So the more, for spikes, the system is going to be more aggressive. When spikes go down, spikes in requests, when they go down, the system is going to use humans a little bit more. That's the beauty of it. I promise you, people, after you explain these companies, the next question is, when do we start? I promise you, that's what they do. Like, what do I sign? Because they see these 100% aligned with what you're doing. You're not trying to replace their workforce. You're not telling them like a magic, well, we're going to have a model that's magically going to reduce all of their work that you have. You're not. You're speaking their language. Let me see the Q&A here. Christian is asking, cost-sensitive human in the loop is evaluating costs of a mistake only, correct? Yeah, this one here is just taking into account the cost of mistakes. That is not necessarily the only thing that you could do. You could have values for true positives and true negatives as well. So not only mistakes, but it really depends on the use case. In this particular scenario, the cost of a true positive is 0. Like you have to do it. You cannot sway the model for saying that you only care about the mistakes in that particular case. DJK.
A quick general question. Would you call this process a fine-tuning or?
No.
Okay. Thank you.
So fine-tuning is when you modify the weights of a model. When you take a model and you start with a model that was already trained, and you're going to modify those weights so the model provides different answers. This could be seen as a fine-tuning of a system. That's fine, I guess, but that is sort of like escaping the actual definition of the term fine-tuning, which is related only to models. Does that make sense?
Yeah, that's what I'm asking. Yeah, like ultimately it can lead to fine-tuning because you're collecting more data, you can retrain. But this process overall, you will.
So I would call it fine-tuning in the sense of the English term fine-tuning, not the technical term.
Got it. Thank you.
Makes sense? Yeah. Keller.
It seems like one thing missing is the accuracy of the human, and maybe this is assuming the human is 100%. Am I right with that?
Yes. Yeah, humans are not necessarily 100%. So there is a risk when you send to a human. The assumption here is that not necessarily that humans are 100%, is that humans are better at this than you are. And that assumption is not necessarily true. At least it's not going to be true all the time, okay? So there are cases where humans are worse than the model, but you have to use them just for, the model cannot scale more than what we're using it. The model is too expensive, so let's use humans. But usually this is the model that you should be thinking about. Like the human is going to be better than the model, therefore we're going to rely on the human. You will not rely on a human if the human were worse than the model. You will try.
In terms of the formula, would you want to incorporate the human accuracy?
I see what you're saying. Like you could like if humans, let's say they're 98%, you could also incorporate that here to just adjust the formula a little bit more.
Okay.
That like the cost will not just be 200. The cost will be, well, what is the potential of a mistake? Like 1 minus 0.98% for the human, because humans are 98%. Yeah, you could do that. Yes.
So I had a similar question. I'm assuming there will be some kind of qualification or verification in the backend, right? So there's some kind of process built.
What do you mean?
Like if the human makes a mistake, somebody can catch it and fix it.
Oh, no, nobody will.
No.
The human here is sort of like the human is usually like the ultimate voice. So that they are the ones providing ground truth. And yes, they will make mistakes and you're going to have to live with them unless you have like a reviewer of the reviewer. Unless you have a human
Right.
on top of a human, it's just no way to catch that. Yeah. Mark.
In the greater loop of your pattern, the data humans get to relay to analyze is high quality train data for the next cycle or test data.
Right.
Right. Do we introduce some feedback loop here? I'm not sure myself to think the right way around for that, where we might overfit the whole system, not only the classifier, but the whole loop somehow. So that is there, I cannot completely think through it currently, but it's a loop, and do we have a problem here?
I'm not sure. Like, I'm not sure what are you thinking? Like, what loop could cross over?
We let the classifier or the cost matrix at the end. Oh, sorry, it's emergency. Sorry. Just go on.
Okay.
I write it in the QA later.
Okay. Ahmed.
Hi, Santiago. Another question: how we can get use the answer from the decision? Can we have it just like to make it more useful and use it for in a certain point in the cycle, for example, for the evaluation or something? Just another loop, just to evaluate the decision from each scenario, so we can have like a stretch each scenario, for example.
Can you give me one specific example of what you mean?
Yeah, for example, if we know that we send it to a human and the human decision was wrong, for example, or we send it to.
How do you know the human decision was wrong? You mean asking the model to evaluate the human decision?
Exactly.
Yeah. So there are ways, automatic ways, to detect incorrect labels. So just whole papers have been written about that. I can give you one specific library that does that very well. It's called CleanLab. CleanLab. That's the library. Just look it up. It's just a GitHub library. There is a whole paper behind that library. CleanLab, you can run it on a data set, and CleanLab will detect when humans provided the wrong answer. So it will do, some sort of like analysis, and the paper is super interesting. I don't remember anything of it, but Thank you for the GitHub there, Mark. But they can detect that, so they can find mistakes in the labels. Okay, that's what you will do. It is, Mark, it's pretty mind-blowing. And when you hear about it for the first time, you're like, no shit, there's no way. It's yes way. There is actually, they are PhD students. The one who created them, created the library, MIT students, and they even teach at MIT a class that's called Data-Centric AI. And you're going to be able to find that class for free online. Maybe MIT or Stanford. I don't remember right now. But if you Google Data-Centric AI class, it's going to come up. And the authors of the library, they teach that. It's MIT. Okay, great. So it's pretty cool library. So you could do something like that, Ahmed, to just detect when humans are making mistakes. You could do that, yes. Julian.
Hi, Santiago. I was wondering if for the basic models, have you replaced the basic models for an LLM? And is it works well, or how it comes?
Yeah. So we talked a lot about this yesterday in the office hours. I know those are long videos, but just in case that you want to go a little bit deeper, I would recommend you listen to the office hours yesterday. It really depends. There are certain use cases where an LLM, it's going to provide good enough answers. And that's the way I usually think about it. But an LLM could be good enough to solve specific problems. Therefore, you would not need like a specialized model. Anything related with text, usually LLMs are going to be awesome for that, especially when you want to do things that are general purpose, like summarization or even translation, or things like sentiment analysis. An LLM, they're very good at that. And unless you're working with a very specific subset of the language, you're probably better off just using an LLM than a custom model. When things get a little bit tricky is when now you're working not with just general text, but text that's specialized somehow. Like an LLM is great at answering questions about law, but it sucks at answering questions about California law. Do you know what I'm saying? Like now it's very specific, and the LLM, it's not gonna be like a purpose-built model just for California law. And California law, what I'm making something up here, it's just talking about something specialized area. There are other use cases, especially non-text related use cases, where LLMs are just not gonna be great solutions. An LLM, take the Penguins data set and ask the one in the code walkthrough. If you ask an LLM to provide predictions, it's just not gonna be good at it. It just does not know how to do that. The LLM can build the model that does that. It cannot just provide predictions by looking at a table with columns. It doesn't know how to solve that problem. So you cannot just replace that neural network with an LLM. You need a specialized neural network for that problem. Hopefully that makes sense.
And for your example with the Californian law, context will not solve or mitigate the issue? If we say, okay.
Right. So it could solve it just with context. It was just a bad example, but the point is, so think about it like as a general rule. The more specialized you get, the least effective the LLM is going to be. The LLM is a generalist, so it knows a lot about everything, but it's not specialist at anything. It's not great at very obscure particular use cases. Also, it really depends on what you want to use that LLM for. So let me make it a little bit more complex. If you want the LLM to just tell you California law, then yes, maybe the LLM is going to be good enough if you provide the context, if you provide the law, and the LLM is going to parse through it. If you want the LLM to act somehow, to maybe, hey, how would you argue for this particular trial? Help me argue this trial. Now it's a whole new ball game. It's not just about reading the law and telling you what applies. It's about it's about giving recommendations on how a particular lawyer should argue a case. Now,
How to build the case, yeah.
Better, Dinesh.
Yeah, hi Santiago. Just an extension of that, follow up to that particular answer. So basically, we apply AI for predicting a price, predicting whether the gauge is the prediction class problem, and then we also do apply for the classification problem, whether it fits under this classification or not. And then there is also another other set of things where product recommendation and the related products recommendation related. So do we apply LLM there, or we skip it and we apply like other principles there?
Trying the LLM, and this is what we talked about yesterday, trying an LLM is usually very simple. So I tell people, why not just give it a try?
Yeah.
The question is, you need to know when to stop. If it doesn't work, like how much more time you're going to invest on something before you decide this is not a great solution. But using an LLM, the barrier is so low that sure, just give it a try and see what you can get out of it. Yeah.
Okay.
This is like you are going to build like a third sense about which problems are good for this type of model with time. Before you build that, before you have that, you have to build it. Like you have to come up with that. And try it is the best way. Try it, doesn't work. Now, the next time, maybe when you see a problem that looks like that, you're not just going to waste your time. You know that's not a good use case for that.
Okay, cool.
Kevin.
Oh, sorry, I forgot to unmute. Maybe you mentioned this. Apologies if you did. For the cost-sensitive evaluation, is that like a model itself, or can that just be more of like a static, component that you just sort of like implement, with normal
static
programming? Okay.
Or compute the costs and making that decision. This is just static. You're just using a formula to just make a decision here.
Cool. Okay.
Not it for a model. Yeah. I mean, it could be a model. Like in this particular case, I think we talked about using this step to check past whether we've seen something like that before. That would be, we could be using there an embedding model. So part of this check would be using a third-party model just to check generate embeddings and check for similarities. So yeah, it could be a model there, but in this particular case here, which is the cost-sensitive case, here I'm just applying a formula. There's no model here made. Cool, awesome. So 2 more sections here and we're done. The first one is going to be model compression. I'm going to move fast to this one here. But I just want you guys to understand that some of these models, when they come out of the factory, they're really, really big. And deploying a model that's too big, it's very costly. Sometimes you cannot use it. Again, think about a self-driving car. When you need to prioritize speed, you need results that are really fast. You have to compress these models. In fact, there is a tweet a long time ago. I had it in one of my slides from Elon Musk explaining exactly what was the quantization process. That's the term, quantization. We're going to talk about that in a second. The quantization process they went through for their model. So a few techniques that you might have heard of, or at least I want you to have them in mind to optimize these models, to compress these models. The first one is pruning. And pruning works, it's very simple. Imagine that you have a model that looks like what you have on the left. With pruning, we are going to detect any neurons that are not having a lot of effect in the answer, and we're just gonna get rid of them. Basically, you go through a model that has, let's say, 10,000 weights and biases, and it's gonna come out with 500 of those. Well, 500, that would be like a huge prune. It's gonna come out with 6,000 of those, or whatever, 80% of those, like 8,000. Basically, you're getting rid of anything that is not contributing to the final answer. And this is not free. Not only it takes a long time to prune a model, you also affect the accuracy of the model, because a weight and a bias, like specific neuron here, parameter, might not be contributing a lot, but a lot is not necessarily zero. Meaning, by removing those, you might be affecting the quality of the answers, but it's a trade-off that you are willing to pay, okay, in order to get like a smaller model. Quantization is one of the most popular ones. And basically, the whole idea here is dealing with precision, the precision of the parameters of your model. Let's try to sort of like, let's see if I can explain this quickly here. But imagine that I have an original matrix. This is the matrix of my model, just to simplify it. I have all of these values that are 32-bit, okay? So I have a ton of values, and I'm using 32 bits to store all of these values. They're float values. And I can replace this. I can quantize this to this matrix plus an index that looks like this, okay? Now, this matrix now is only 2 bits. Each value here, only 2 bits. Before 32 bits, now only 2 bits, okay? So this is sort of like the way it will work. Notice that I have like a negative 0.1 here, and I'm replacing that with a 1. And if you look to the 1, it's going to tell you that this is going to be a 0. So any value that's close to 0 is going to be replaced by a 1. So that's why I have negative 0.1, that's a 1, 0.1, that's a 1, and 0, that's a 1. And again, a 1 is just the value is going to be 0. It's an approximation. Let's look at the other one, this 1.0. It's going to be replaced with a 3, and the 3, it's going to be like, it's going to be rounded to 1.1. So anything close to 1.1 is going to be replaced with a 3. Again, it requires only 2 bits, 1 and 1. Those are the 2 bits that it requires. And you can go throughout the whole matrix and see how this is crazy, how much compression you are going to get. The downside, obviously, is you're rounding the values. The values are not, you cannot have the precision that you had before. Because before, this number and this number and this number were all different. Now they're all the same. The new model has all of those numbers being the same. That is going to introduce errors. Mark.
As an intermediate step, couldn't we just say, oh, we multiply, or how do you say, add a certain, multiply and add some value to get them all higher than 0, and in the range between, let's say, 0 and 255, to get rid of 24 bits? Or does that not work?
I mean, there are multiple ways that you could read. If what you're thinking about is how can I just reduce this 32-bit here to make it small, right? Yes, you can just, basically round up all of the numbers and make it even smaller and smaller and smaller. I'm just showing you like a drastic way of doing that, of going all the way from 32 to 2, right? And the way you do that, again, is just a matrix. Each value has 2 bits, and then you have this table here. Now make this matrix 1,000 by 1,000, and you will see how much you're gonna save from 32 bits to 2 bits, right? It's literally 6 times smaller.
But this will introduce computation costs, right? Because we have to do the transformation.
Every optimization is trading off quality. You're getting a smaller model, you are getting a faster model, you're getting a cheaper model, but you're getting a less effective model as well. So
why is it? I didn't get why it is faster. I would assume instead of having that values, we have to do the backwards operation through the quantification matrix to get to the value.
You mean, like, why is it faster? Is that what you?
Yeah.
Well, if you have less parameters, it's going to be faster to compute. In this case here, you're not necessarily having less parameters. You are having less parameters here.
Okay, you talked about the general case, not about that method.
Right. So imagine that I have a GPU. If I have simpler operations in that GPU, those operations are going to be faster to compute. So of course, this is going to be faster. It's going to be smaller as well because I don't need as much memory to store that model. At least I need 16 times less memory to store the model here on the right than the one that I have on the left. So that's why it's going to be smaller, but it's going to be less accurate here.
If the values repeat a lot, I can see, at least in this simple example, that you could do some lossless quantization because you didn't need to round. But I guess in the real life, that's not that efficient.
So we're talking about billions of parameters, right? So imagine that you have like Llama 4 with 270 billion parameters. So it's gonna be a lot of values there. And you can quantize, you can be more aggressive with quantization, you can be less aggressive. I mean, you can, in the extreme case, you can turn all parameters to the same value and be done with it. And you literally have nothing, like this my model, and it's also gonna be, that is also not gonna work. You have to find that balance there. Yeah, you die. I don't know what to say.
I think this, I hope you can hear me. I think this is exactly one of those things. Humans tried something and it worked great. Even though it may not make a lot of scientific sense, which is probably where everybody is trying to figure this out. But it was one of those things where you went from floating points to integers, and man, you didn't lose much of the quality, but you gained magnitudes of speed improvements. So this was one of those things you said to try.
Elon's tweet was something like we went from float 16, so 16 bits per value, to int 8. That's sort of like the step that they took. So basically, they cut it in half, the amount of memory they needed for one of their models. They cut it just basically in half. DJ?
For multimodal multimedia generation, would the end user notice the difference in image, audio, video?
It really depends. So ideally, it's just minimum, but again, it's hard to say whether the users are going to notice something based on quantization. I can tell you that the more aggressive the quantization is, then definitely yes, users are going to notice that. If it's for image generation, music, whatever it is. Because again, the extreme case is a model that does not work. It's so optimized that it doesn't work.
Yeah, you need to find some sweet spot. Yeah.
You have to find that sweet spot, right? That where users do not notice it, but you can still have a business. You can still run that model. Yeah. Okay, so the next one, and then I'm going to go to you, Mark. The next one is knowledge distillation. This became popular again with large language models. This is a little bit more complex to sort of like understand, but the whole idea here is that you have a teacher model that is the big model. You train a big model, it's huge, and you're like, holy shit, I want to make this smaller. And then what you do is you train a student model, a different model, smaller model. You train it to mimic the teacher, not to solve the answers, but just to mimic the teacher. Okay, so think about like the regular training process of a model. You show it one example and you tell the model, hey, this is the example, this is the proper answer. And that's how you train a model. Now here it's a little bit different. Here you're gonna say, the student model, you're gonna train it by saying, here is the example, this is what the teacher said, and this is the right answer. Okay, so notice that there are two losses here, okay? Two different losses here. One loss is called the distillation loss, is how different your answer is from the answer from the teacher. So you're basically adjusting the student to do the same that the teacher did. That's what you're teaching the student on. And there is another loss, which is the cross entropy loss, which is basically how far away were you from the correct answer. And you combine both losses, and that's how you train the student. If you did not understand any of this, don't worry, just not necessary. Idea here is you're teaching a model to mimic another model. The beauty of knowledge distillation is that it has been proven that doing this can get you better results than just training a smaller model on the original data set. Okay? Like if you try to train a model, small model on the original data set, you will get worse results than if you try to teach a model to mimic a bigger model that's very good, which is super interesting. Mark?
Are there any like rule of thumb, like compression limits that you have offhand? Like, oh, don't try to compress down to like further past like 20% of like a large model size or something like that?
I don't have any numbers like that. I'm pretty sure for different use cases, people will know what those numbers look like. The way I do it is, number one, optimization is that. It's an optimization step. Do you even need it? That would be the first question that I will ask. Don't try to quantize a model if you don't have a problem with that model. The problem comes when, for example, you have a lot of requests. You need to reduce latency because the model is really slow. So at that point, now you start looking into quantization. And the question is, what is the minimum that you can get away with? Like, let's just take a little bit off of this model so we get into the good grace of the hardware gods. Don't try to just quantize too much, right? Quantizing is a bad thing for the model. So you don't want to do that unless you have to. Does that make sense? That would be sort of like the process I will go through. Quantization, by the way, or this optimization, there are two ways of doing it. I would say three ways. So the first way is you train a model that's small enough from the beginning. You don't need to quantize. So instead of trying a model that's big, you could just try to train a model that's smaller from the beginning. No quantization necessary. That would be the first way that I would try to approach this. For example, you're building a model that's going to be running on your phone. Don't take a 10 billion parameter model because it's not going to fit in your phone. So it's not about training a big model and then trying to quantize it. You're not going to get good results. Start with a smaller model and train that model. Second way is you do quantization aware training. So that means even before you start training your model, you are already using int8 instead of float32, right? So it's the whole process is going to start already with a model that's quantized. And the third way, which is probably the most popular one, is when you train your model and at the end of the process, you quantize it, you optimize it. That would be the third way. But again, all of these are optimization steps. Do them only when necessary. And then we're going to talk about the final one, which is low rank adaptation, or LoRA. This became popular, a lot popular with large language models. Is also a way to do more than model optimization. And I think it's magic. It's one of the beautifulest ideas. It's one of the things that you are happy you're alive to see people coming up with shit like this because it's so amazing. This is the way it works, okay? So imagine you have a freaking big model. And I'm going to take the example of Apple because they wrote a paper that they were going to use this, and I was so happy. And then I don't know what happened there. But imagine that you have Apple. And Apple builds a big, large language model for their phones. It's big, but still fits in your phone. But this is just one generalist model. But they want to use this model to solve a bunch of smaller problems. They want to do summarization. They want to drive Siri. They want to write for you. They want to analyze images and do, right? And all of those AI tasks, they want to do in your phone. There's no way they're able to build specialized, big, large language models for each one of those tasks because you don't have the space or the memory to run all of those models. So what do you do instead? Well, you take the generalist model, okay, and you do LoRA. And what LoRA creates is this adapter, okay? So think of the adapter as these two pentagons that I have. Are those pentagons? No, they're not. What are they? How do you call them? Parallelograms? No. How do you call this figure?
Quadrilaterals.
Trapezoids.
Trapezoids. Quadrilaterals.
I have no idea what you guys are saying.
Trapecio en español.
Okay, so Okay, so that's a trapezoid. Okay, trapecio. Okay, cool. So anyway, my geometry is at 0. So these two trapezoids are the adapter. Okay, so think about the adapter the following way, and then I'm going to explain how it works. So we have the big model, only one copy of it in our phone, and we have multiple adapters that are capable. Those adapters is like an injection of specialties. So you have one injection to the big model, and now the big model knows how to process images. And you swap the adapter you take another adapter and you plug it in on the big model, and now the big model knows how to summarize text and knows how to write text. See what I'm saying? Just by swapping the smaller adapters, you get your model to act differently. Wouldn't that be awesome if that were possible? It is possible, actually. And this is the way it works. So what we do is there is a process of fine-tuning in the middle of it. But instead of taking like the big freaking model and fine-tuning the model, we're just going to fine-tune the adapter. So the adapter is the one that is going to contain the information that's necessary to, when multiplied with a big model, change the behavior of the big model. Why is that possible? Well, because we discovered this low-rank factorization thingy, which is freaking magic. Look at this matrix. There are 25 values in this matrix. This matrix I can represent only with 10 values. So this matrix is the product of this vector with this vector. You don't have to do the math, trust me. So if I take these 10 values, I can represent these 25. And the ratio gets increasingly crazy. 1 billion parameters you can represent with just a few values. A multiplication of 2 vectors can get you like a huge matrix. So that means that I can only have, like I can take like a huge model, a big model, and create these 2 trapezoids here, these 2 vectors. I can have these 2 vectors, and I can optimize those 2 vectors and store those 2 vectors, which are really small compared to the big model. And at the time of running the big model, I can literally take these 2 vectors, multiply them together, get this matrix, and take that matrix, multiply it with the pre-trained weights, and completely transform what the model does. So it's a very neat trick that will allow me to adjust the model or compressed like specializations that I can use together with a big model to completely transform what that model does. Pretty neat. I'm going to leave it at that. Just look it up. Look up for LoRa, and you're going to find a bunch of explanation of how that works. It's a freaking beautiful thing. One more chapter, and let me check the questions. I'm sorry. Let me see. Do you feel that coding, especially code reviewing, is something that a general LLM can perform out of the box, or should one do something more tuned or specialized for that? I like if these LLMs are good at something, is code, not only code writing but also code reviewing. So I would try to use a model like that. Obviously, if you have the means to specialize an LLM in code reviews even more, maybe you can get better results. Is BERT and DistilBERT knowledge distillation implementations? I'm not sure exactly how you would define them. I can tell you they are pre-LLMs. I would be surprised if people are using BERT and DistilBERT right now instead of just using an LLM. I think they're pre-LLM. I might be wrong there. I'm not a specialist in natural language processing, but those two come before LLMs. They might be now, I don't want to say obsolete, but less useful. And again, correct me if somebody knows that what I'm saying is just crap. Just correct me because I'm not sure. If we quantize different areas and even individual weights are differently sensitive to the loss of resolution, is there a way to analyze which are and aren't? Yes, there is. And pruning is exactly what that is. So pruning, imagine pruning is like quantization. but instead of changing the precision of all of the weights, you're literally getting rid of anything that does not provide value. So you could argue that you can do pruning and then quantize the rest. You could do that to be
Or
even.
if I get too much loss on a prone, I take it in and try quantizing instead for that specific value.
Yeah. So LoRa is like dependency injection for machine learning. I've never seen somebody put it like that, but it kind of makes sense what you were saying. So I'm gonna say yes. It's like dependency injection. All right. So the final area that I want to cover here is specifically about catching. A bunch of you asked about catching and different catching strategies. I'm going to try to keep this high level here, but hopefully everyone understands the importance of catching. There is a famous saying that says there are two hard things in computer science. Who can tell me the rest? Two difficult problems in computer science. What is the first one?
Naming variables.
Naming things. It's the hardest problem in computer science, naming things. And the second one
is cache invalidation.
Cache invalidation. Basically determining when something that's in cache should go away and you should not use it anymore. So it's a very famous saying, computer scientists know. So naming things and cache invalidation. And the reason cache made it to the top 2 list tells you that cache is very popular, very useful, right? So that's what we use it all the time. Now, whenever we're working with these systems, there are usually 2 strategies that you should take into account. The first one is what we call it exact catching. And this is very simple to think about. This is if somebody asks me about who's the president of the United States, I'm just going to return, I'm going to save that and I'm going to return that. That's exact catching. If I find the same query, I'm just going to return the answer for it. So here's the way it would work. So imagine that I'm going to have a cache component at this step right here, and the user is going to send a query, and this cache component is just going to check and say, is it hitting the cache? Like, has anybody else asked about this before? And if the answer is yes, then it's a cache hit. Therefore, I'm going to just return the answer right away. And I'm not going to engage anything else from my system. Like, I'm not going to go to the model. I'm not going to do anything like that. You could have it here. You could also have it as part of the model gateway if you want to, okay? But it's fine. You can have it at different levels depending on what you want to. If you send a query and you have not seen that query before, that exact query before, then you would say, well, that's a cache miss, so I'm going to engage the rest of my pipeline, which, everything else is going to happen here. By the way, obviously, when you have a cache component like this one here, you need to make sure when you provide an answer to store that answer in the cache, so the next time you can reuse it if you want to. So that would be how you will implement exact catching. Obviously, very simple to implement, also ineffective, especially when the input to your system, it's open-ended, because you're going to be less likely to find hits. Like, maybe you ask, who's the president of the United States? Maybe I ask, who is the current president of the United States? And now that's going to miss the cache, right? Because you usually need a character for character match for that to be effective. And that's where you implement what's called semantic catching, which is another popular solution that you can do in order to increase the amount of cache hits that you get, okay? This is the way that will look like. So notice how the cache now became way more complex. You send a query, you're going to have an embedding model, and that embedding model is just going to embed that query and use a retriever to return similar answers from a vector database. And now you can get a similar answer and determine, is it similar enough to the query from the user? And if the answer is yes, then that's a cache hit. So I'm going to return the answer. If the answer is no, that's a cache miss. So I'm going to engage the rest of my system. By implementing this, this is sort of like the same components that you would use in a rack system. Now you have a way more robust cache. Does that make sense? Obviously, there are trade-offs because there are no silver bullets in computer science. There are always trade-offs. The trade-off here is that this is slower, way slower than a solution without the cache or than exact cache. Because here, for every query, you have to generate an embedding and you have to return data from a vector database. You have to query the vector database. And that introduces extra latency. Okay? It also depends on those embeddings to be good enough, to be well-tuned. It also depends on you to understand the similarity, how similar something should be in order for you to return an answer. Okay? So maybe there is something that looks similar, but the answer is not correct. So you're going to be giving an answer that's incorrect to the user because your cache was not well-tuned. Caching also has other problems like security. Be very careful. If you have a system that returns information that belongs to a user, you gotta be careful you don't return that same information to a separate user. Because that is how things get really, really out of hand. I've seen these like publicly play out on Twitter. Like I asked something and I got an answer back that's not my data. Like who's what? And it's a cache, a cross-pollination here across different users. So caching, not free. Okay? So it's great, it's awesome, can improve the latency a lot, but it comes with certain risks and with more complexity. Again, it's one of those steps that you add in order to optimize your solution. Okay, so that's the last slide I had for today. I'm only 3 minutes over the time, so that is a new record. What questions do you guys have? Amen, go ahead.
Hi, Santiago. When it comes to the serving of the model, I have a question regarding if there is any, for example, if the customer or the client asks me to build a system that is not connected to a cloud, for example, or they need a model only in the local machine. Is it possible, or we can consider like areas without internet connection or a rural area? So
yeah, if you don't want to cloud, the question
Mm-hmm.
is where are you going to store that model? Where are you going to run it? So you could have a model running on your computer, I mean on a computer that is not connected to the cloud. Yeah, if that's your question, yes, it is possible. That comes with trade-offs, obviously. Like, you know, that model has to fit the memory and the hardware requirements of that computer. And obviously, local computers that are not servers, they're going to have less requirement. You can also build a server if you wanted to. Just have a server sitting somewhere, a big server, and you run your model off of that server. Is that what the...
Yeah, and if we have any update on the model or something, if there is any recommendation, for example, just to keep the system and the local machine updated as well, or
yeah, you're gonna have to create the update flow for that model. Like whenever you put a new version of the model, how are you gonna update the existing model? You have to create that. That doesn't mean that you have to be connected to the cloud. You're gonna need connectivity, obviously, but not necessarily to a cloud provider. This doesn't needs to be hosted on AWS or GCP or Azure. You can have it in your own infrastructure, your own hardware. But yes, you're going to need a way to update the model. Yes.
Okay, another question regarding the cost sensitive, because in your example, it was something with the maintenance, for example. But because I'm coming from the medical field, or if we have to apply this to the medical queries, for example, or medical decisions, how it's going to be the equation, for example, to calculate the cost matrix? Because it's a decision for a life or that, you know, just like.
So that's one of the reasons I always stayed away from health. So in a cost-sensitive scenario, if you wanted to apply to health decisions, then you can quickly get into the point where somebody has to compute what is the value of making a mistake with a human life. And that is not something I even want to discuss. Not every scenario in the medical profession is related to human lives. Like, what is the cost of telling a person that is going to die from cancer versus the cost of telling them, and it's not true, versus the cost of telling them that they will die from cancer, or the other way around. You get the idea. What is the cost of telling a person you are not going to die versus the cost of telling a person you are going to die, but it's not true. Okay. And you can argue that, telling a person that is going to die when it's not true is less costly because they're going to find out anyway. They're going to go to another doctor and they're going to find out and they're not going to die. But if you tell a person you're not going to die, you're fine, and that person has cancer, well, they won't do another checkup. So again, you get into these scenarios, and what is the cost of making that mistake? Infinite? Like, are you going to put a cost? I don't know how to apply that to those scenarios.
Yeah.
So, very not nice. Yeah.
Yeah. Okay,
But
last
the
question.
formula,
Yeah.
assuming there is a cost, which I'm not going to tell you what I think it is, but assuming there is a cost, the formula will stay the same, right?
Mm-hmm. Yeah. And also regarding I think the slide before, it's just like for the feedback of the response, can we consider the response without the feedback like a hallucination in this case? Or it's, if we didn't, I think you mentioned that in the slide. So is it kind of hallucination if we keep the system without this feedback loop? Just giving answer without any...
A hallucination is just a mistake that the model makes. So every model will make mistakes. For LLMs, we call them hallucinations. Regular models, we just call them mistakes. The model provides an answer that is not true. So the whole idea of adding these checks and involving humans is protecting against those mistakes. So imagine that you're using a large language model. Your large language model will have hallucinations, and you just need to understand, should I trust the answer from the model or not? And one way of doing that would be, for example, checking whether that model has answered specific topic before and how did the model do when they had to answer. So if somebody's asking about baseball, we're gonna see, has this model answered about baseball before? And if the answer is no, I have no reason to trust the model. The model might be hallucinating. Therefore, I'm going to involve the human to provide that answer or to review the answer that the model gave, which is the same thing. That's the entire idea here. Is all of it is taking into account the possibility of a model hallucinating or making a mistake.
Okay, thank you so much.
TJ?
Yes, another quick question. I heard the terminology called MOE, mix of experts. Is this something you're going to cover later? Is this seen as optimization?
So yeah, no, we're not going to cover it, but the idea of a mixture of experts, think of it like you get a query, you get a router, and the router decides who is the best position to answer a question. That will be sort of like high level what a mixture of experts will look like. But in the case of the specific case of mixture of experts, that's an actual architecture of a model, how you train it. So it's not the same as having multiple models working together. I'm not going to cover it. That's a very, very, down in the weeds concept, but you can Google it up. You can learn about it. But it works like that. At a high level, it works like having a router that decides which expert I'm going to ask to answer this question. So imagine you get a math question, and instead of just using a general model, I'm going to say, hey, I'm going to get my model that specializes in math to answer that question. And if I get a question about physics, I'm going to go to the physics model. That's what you would do.
All right, so the framework of router is still used for this purpose, correct?
The idea of a router.
At lower level.
Yes.
Got it. Another quick question. How interoperable are the models? Say, can I host OpenAI model on Google and vice versa?
Yeah, they are very, but not necessarily one for one. There is a library that would recommend if you wanted to just make sure your code is fully interoperable. It's called Light LLM. When you use Light LLM in your code, you can actually connect any model on the other side. Light LLM will take care of the differences. So there are differences. OpenAI came up with an API because they were first, and every other model is now trying to follow the same API. So it looks like you can just swap one model by the other, but not really, because they have different ways to generate things and whatnot. So you want a gateway for sure, and something like Light LLM will help you smooth those differences. So you use Light LLM, and you can easily swap one model by the other.
Okay, and the concept of MCP is completely separate. It's completely different application, right? It's not.
We're gonna cover that next week. MCP is a protocol to connect these models to different tools. That's what you.
I see. Yeah. Thank you so much.
Sure. What else? Open Router, yeah, I've never used Open Router. Yeah, so I don't know how to use it or anything. The one that I've used is this one here, Light LLM, which I'm going to share. By the way, they're not necessarily the same thing, but just
Open Router, you use one API key of them, and they redirect the back. Use a lot of models, so it simplifies and have higher usage rates. Sometimes when you have your own API key, you have a lower rate limit on some things, and Open Router helps you with that. But
okay. Yeah, I've never used it. Glad to know that exists. Yeah, Light LLM is not for that. Light LLM, you have to use your own API keys for everything. And it's just an interface for your code. So basically, you can, instead of calling the generation API from Gemini, you call the generation API of Light LLM. And internally, Light LLM, depending on the model that you're using, knows how to translate that to Gemini, to OpenAI, to Llama, to whatever model. It supports like hundreds of different models behind the scenes, which is great because of that. Light LLM versus LangChain. So LangChain does some of what Light LLM does, but they're not a one. So there is overlap, but Light LLM does, the only thing that it does is this thing that I just told you. LangChain, it includes way more than what Light LLM does. So for example, LangChain can let you put together very easily, connect to vector stores, connect to documents and process documents to do like a RAG system. Light LLM will not do that. Light LLM only takes care of communicating with the model, not with vector store databases, not with different retrievers. It does not implement chunking strategies. LangChain will do all of that. So it's way more comprehensive. Ahmed.
Yes, also another question regarding deployment. Do you recommend any software or something, or just like Flask, or I know because there is Flask or Streamlit, but do you have any recommendation for the deployment?
It really depends. The way I've done it, it really depends on the model that I'm building. Like, for example, if I'm building a PyTorch model, they offer Torch Serve, which will be sort of like the system that you will use to deploy these models to make them available. If you're using TensorFlow, you could be using, it's called TFX serving. So that is sort of like their platform to serve models. In the code walkthrough that I'm going through, I'm hosting the models using MLflow. So MLflow provides some sort of like wrapper to deploy these models. That's what I'm using. So there are multiple different ways. It really depends on what you're building. And that's sort of like going to point to, okay, so you should do it this way. Streamlit, by the way, is not a deployment platform. Streamlit is just a simple way to build UI applications on top of your models. And you know, it's for that. Streamlit, it's closer to what a data scientist will use to showcase their model than what a machine learning engineer will need to deploy a model, right? Machine learning engineer will be using a ton of Docker. These platforms out there, like the cloud platforms, like AWS, for example, if I want to deploy a TensorFlow built model in AWS, they're going to be using a Docker image that is running TensorFlow serving inside. if I were to deploy a PyTorch model, they will be using a Docker image that's running Torch serve inside. So yeah, it really depends on the model.
Okay, thank you.
What else? Tomorrow is Friday. Dang. Tomorrow I have going to Miami tomorrow. Mark, what's up?
Yeah, I mean, as a developer, I mean, one of the really frustrating things I run into is that I'm reinventing the wheel. I focus on a problem and then I find someone's already solved it. So, you know, just talking about the domain of LLMs, are there blogs, YouTube channels, publications we should be looking at to know who's developed what and what the latest techniques are?
Man, the answer is yes, but I don't know where to point you at because there's so much. It's like a freaking fire hose, like drinking from a fire hose there. I don't even know what to tell you. But here is what I personally do, especially when I'm trying to produce work for companies, is that I try to focus on the fundamentals and try not to chase. I try not to worry too much about specialized solutions. What I mean by that is there's a freaking race for everyone to claim that they built the best and the brightest and the greatest. And most of the time, that just produces garbage. It's like models competing for benchmarks. Like everyone wants to be the #1 model in the benchmark. And when you try the model, that doesn't translate to real use cases or things that you can use. So I try to ignore that and focus on the things that we know that are solid, right? The foundation models that are solid, the science behind those, how do I solve this type of problem, type of thing. I know that I'm just telling you general things, they're not specific. But that's what I try to do, try to ignore as much of the noise as possible. And the other thing that you can do is whenever you face a specific problem, at that point, you just do some research and see if somebody else has worked on something similar and what do they do. That's the best advice I have for this.
Thank you.
What else? Yeah, I see. Mark, Paul wrote, check out Hugging Face. That's a very good recommendation. Hugging Face is like the GitHub of models. So you're gonna get models there for anything and everything. So just doing a search on Hugging Face, that would tell you whether somebody has built a model to solve the problem that you have. Yeah.
Thanks, you and Paul.
Yeah, Paul, great recommendation with Hugging Face, horrible recommendation with Reddit. You just destroyed all of your good work there by recommending Reddit. I'm just kidding. I just hate Reddit so much. Don't like it. Uday, what's up?
Guess you're not having many questions, so a little bit of an off-topic conversation, especially some things that you've been posting on Twitter, and I just thought I would share my thoughts. You are, maybe you have a lot of success stories trying to build new stuff. As you point out over and over again, you provide a set of prompts to the agents and you wake up in the morning, ta-da, you got your work done. And then one day just struck me because I've spent my entire life in enterprises, decades, over 3.5 decades now. So you are what we call shadow IT, you know, every business user always wanted this ability, what you're experiencing, the ability to create a new application because they have a new need that is unmet. And guess what happens sooner or later? They have this huge pile of applications. They don't talk to each other. And so all little applications, people don't even remember what they do anymore, but I need it now, so keep it running. So it was interesting to see you do that. And one thing I'm probably going to ping you maybe a year from now to see is how big is your pile of all those little applications? Do you know where they are any further? Like you did something a year ago and you want it again. Is it easier for you to ask the agent to rebuild it versus finding the app? That was something I'm really curious to see how this works out for you. You are creating applications like rabbits at this point in time.
Yeah, but by the way, don't think I have too many satisfactory answers for those questions. I'm just having the same issues. I'm also right now very on the verge of the value of these models. I'm struggling with this a lot. I want to say one thing, but then things happen and that make me question that they are really useful for me. I'm struggling right now with the fact that I really love to write code. It's something that I've always done because, first of all, because I love it, and second, because I get paid. But these models are completely sucking that away. Like, I do not enjoy having these models write the code for me. It's just a fact of the matter. For some people that I know, developing software is just a job and they do it because they have to get paid. That is not my case. Like, if I don't get paid, I will still be developing and tinkering with code, and I just do it because I love it. So again, is it smart for me to just use these models and completely suck the fun out of the work? At that point, do I even want to do this as a career if I'm forced to use these models? But on top of that, are these models really helping me? And I know when they are, and if I want to put together something really quick, these models are great. I can have a solution done overnight. It's awesome, great, that's it for those use cases. But for use cases that take a long, like take this course, the influence of AI in the code that I wrote for this class is minimal. And I've tried, and it just doesn't work. I don't know what to do. I cannot tell AI, build another chapter for the code walkthrough that does it. It just does not work. It doesn't know what it's doing. Or even improve something, it does it, but then I have to go and redo it, the whole thing, because I need to make sure I understand every line of code that I'm going to be putting in front of you. And I need to make sure I'm taking care of all the corner case. I cannot rely on AI to do any of that. So I think right now, the way I'm feeling right now, very weird, is that these models are great at working at a specific stage of a project. They are not helpful at everything else. So we'll see. I think I need more data. You get all of this hype coming from people who for the first time are creating software, and that's amazing. I'm glad they have the opportunity to build things for the first time. But that's just a small portion of what building software is. You understand? Small portion. Anyway, I'm not going to keep ranting, but Dylan.
Yeah, and I guess kind of chiming in on that. I think one of the projects I've been investigating and working on is like in enterprise, we get these requests and they have to be pretty spec'd out, domain models and how we're persisting it. It sounds like, when you're building your ML school project, it's, it can't take in the next iteration. Do you think the enjoyment would come back if you are able to do like, feature based, and, the way I'm kind of like doing is just like versioning the features and trying to build like a specific kind of like Git of requirements and trace it through? Or is it, or you just, really love to drop in and just, and solve the problem yourself? Like, is it purely it can't take it to the next level? Like you can get your, your lovable, your replit spun up really quickly, but then just it's at the after, like the cycle of the iteration after it.
Yeah. It's not about whether the model is capable of doing it or not. What is that's not gonna change. My love is just to and this is weird. This is just me, guys. This is not something that every developer feels or anything. What I really love is the act of creating software, right? The thinking of the problem, the writing the lines, the debugging. I love the process, right? I've been doing it since 1994, long time. Having an LLM that I tell it, just do this, and it goes and does it. Imagine that it does it perfectly fine.
it's just, this is like, just to give you an idea, imagine that now you have a robot that can go and have sex with your wife or your husband. Like, would you use it? Well, maybe if you hate your wife or husband, that would be amazing. Like, sure, just go press the button, just take care of the problem for me. But if you love the act of having sex, you wouldn't use a robot that will do it for you. That would be stupid. This is how I'm not comparing having sex with writing code. I just want to be clear. It's just, I want to, what I want to express is that having a thing that does what I love is just not productive for me, because it's not, I want to do it myself, but I want to just code it.
Yeah.
Obviously, I'm pretty sure that as these models improve, maybe it will be less frustrating to use them. Like right now, I think they are in the frustrating, stage where even if I try to use these models because I want to get something done really quick, they make a lot of mistakes. And now my job becomes just asking them again and again and again in different ways, just trying to sort of like get them to do what I want. Maybe that weren't the case, I will hate that less, but I don't think, it doesn't matter how good they are, I'm still gonna love to write software. So yeah.
And you don't like struggle with being like, dang, like that code is really good. In some cases, you're like, that just spit that out in like 20 seconds. You're like, or you're just like, I could always write it better.
I'm gonna say I can always write it differently in a way that I understand it better. Not necessarily write it better. Like I've seen code that looks good. I always find a way to just improve it for me. That doesn't mean that I improve it. Like you might look at it and say it's objectively the same thing. You just didn't do anything. You just changed variables. But I'm very particular with the way I name things, I organize things, I space that. I know it sounds stupid, but it's not the same thing having 3 lines next to each other that are having 2 lines spaced, 1 line. And those of you who write code for a living, you know what I'm talking about. That extra space there between those lines means something and communicates something. And the LLM doesn't do it. Doesn't know how to do it. It's not gonna do it. And I have to fix it. And it's just, fuck, I have to do it. Right? It's just,
yeah.
We're talking here, like, I don't want to be insensitive to the people who write code. I think LLMs are great. And I want them to stay and I want them to keep helping us. I'm just struggling with that idea a little bit, just because it's doing something that I love. So, yeah.
Thanks.
Yeah. Can you give some tips for job search in US for data science and machine learning for someone with 6 years of educational and professional experience? The market is so crazy. Okay, so I used to love to give this type of advice, especially when I started the class 3 years ago. I want to be careful now because I've been out of the market as looking for a job for a long time now. So I have no idea what's out there, okay? But I can tell you how I used to behave and what worked for me and what didn't work for me. Number one, I used heavily used freelance platforms like Upwork. They gave me a ton of jobs. I got a ton of jobs through that platform. The reason I got a lot there because it's a platform that highlights my abilities very prominently in the search space. So when a company is looking for somebody with these 3 skills, my name popped out. I got a ton of calls from there. What I would do is, number one, try to equip yourself with practical solutions. So basically, when you go to an interview, a lot of people go in a defensive position. They go to, I'm going to try to answer the questions that they ask me, try to be a little bit more proactive. And if you're equipped with solutions that work in real life, that employers tend to like that a little bit more. What I mean by that is that somebody's going to come and say, hey, how do you build a multi-class classification model? And you answer that question, and then you go on the offensive and you say, do you guys have a multi-class classification model here? Okay. And how are you deploying it? Have you considered this? Are you doing error analysis? Oh, yes, you are. So what was the last time that you found that? And how did you solve it? Oh, I have an idea to solve that, right? Try to drive the conversation. That is a trick that I've used and always worked wonders for me. Obviously, this is after you got a call. If you haven't gotten a call for an interview, you cannot drive the interview. Build something that you can show. One thing that I did was building my Twitter presence, like my public persona, and I still do share a ton of stuff that I'm learning, what I'm doing, advice. That's why you guys are here in the class in the first place. You met me through that, and a potential employer would also see that. So if you do that, this is a long-term play, but if you can do that right now, in 2 years, you're gonna be glad you did it, because that will give you a lot of credibility and a lot of networking. That's how you find jobs. I don't know, there's too much to say about this. Again, I do not understand right now the market. I know I've heard from people it's brutal. So I'm not trying to just, I don't know what to do about that, because I haven't found for a job in like 3 years now. So I work for myself. So that's why. This might be a basic question, but I'm genuinely curious. How did you learn everything you're teaching from 0 to 1? I'm working on the fundamentals to grow in the AI field. So I'd really appreciate any advice or guidance you can share. So I started coding when I was 14. That was back in 1994. I I finished my middle school, then went to high school. In high school, I did competitive programming. So that was at the morning, afternoon, and night, just algorithms and data structures, I went to a bunch of competitions, national competitions. So I learned a lot about programming back then. When I went into college, this was the only thing that I wanted to do. So I went to computer science. I mean, it's information technology in my country, but it's the same idea of computer science. So that was 5 years of me doing that. In the middle of my college degree, I started working freelancing. So I started working with companies, making money. That's just fast forward till today. That's what I've done for, 30 years now. 1994, 2025, 31 years. Most of what I've learned, I returned to college in 2015 to Georgia Tech for a machine learning master's degree. But it's a combination of working and studying. That's how I got here. I don't know if I can tell you from 0 to 1, other than this is something that I really love, and I try to solve problems using it. That's how you learn. And it's just a matter of time that you're gonna get better and better and better at it. Right? That's what it is. Most of what I teach you here is stuff that I find while working with companies, and I find interesting. I'm not teaching you things that I have not done, because I don't know how to do them well. I might be able to read a book, but that's not teaching me anything. That's just telling me you should do this or that. But if I try to build something for a company and it works and it doesn't work, I can tell you here what I did. That's the way I go about it. Mark.
When I'm listening to that, I know that in my 40s, I will not recreate any of that lifelong experience for me. But what I want to start is to use that knowledge, what you have to start with one idea, one application, no matter if it's solved 1,000 times, and learn from it. I think that will be the approach of mine. But I do need, and I hope you can help me there out, the stupid beginnings. So what combination of tools should I use when I want to do it on my laptop, because I cannot own a server? What are the free models? I'm a Windows user. How will I survive the transition to Linux if necessary? Things like that.
Yeah. So
I have quite a clear idea of what I want to do, no matter if it helps anyone or not, but for the learning experience.
Yeah. So yeah, great question. So first of all, something that I've learned is that you started by saying I would not be able to reproduce what you've done because it's lifelong. I'm 40 now. I don't have 30 years to just start from like you started, right? Well, sure, but you don't have to, right? Like you don't have to be successful in life. You don't have to follow anybody's path, and you can start whenever you want, right? So first of all, try not to compare to other people. It's not going to be productive for you at all, right? Or it's going to discourage you. That's what happens to me when I look at other people that are doing stuff like Newton. Like Newton, if you look at Newton, he went and discovered the laws of motion, and then he came up with calculus and integrals and all. He made up the whole calculus field was invented by him, and he talked about the planets, and then he turned like 25, 26. And look at that. Fuck, what? He did all of that before he was 25 years old. Like, it's really depressing when I look at my life and compare it to him.
Yeah,
So,
and then he go to mystics because there was nothing to achieve anymore.
the guy is just a freaking genius, right? It makes everyone else look like horrible. But what you're asking is, like, how do I start? So this is my recommendation for my kid. And some other people get mad at me when I say this, but I'm going to tell you. The most important thing is that you really need to find what you like to do. And there are many, many things within the umbrella of computer science, many different things. You need to find what really gets you off bed and trying to build something. If it's a job, you're not going to be good at it. I'm just going to be honest with you. Okay. If for you, it's just a job, something that you have to do, it's like exercising.
There is something. I check.
If you like to exercise, you're going to get fit. You're going to get ripped. If exercising is like, holy shit, I have to, you're never going to get fit. It's just, you're not into it.
I have a checkbox for that already. It will not work with my job. I will have to fight for every minute I can invest in it, but yeah.
So find what you like. And the way you find what you like is by trying many, many, many different things until you identify what pulls you in. So what I mean by that is try Python, try to build web pages, but build something, not just read about it, just build something. Just find a little problem, small problem that you can solve for you, just for fun, and build it. I know a lot of people that they build circuits at their house where they connect an Arduino with the camera just to get the camera, take pictures, or like whatever. It's just a hobby, right? If you do that, and you get exposed to many different aspects of AI and graphic design and all of that, you are going to notice that you're getting pulled towards certain directions more than other directions. Like, I've never got pulled towards the web, for example. I don't care about the web. I don't like to build web pages. That's not me. Or mobile applications. I don't like a mobile application. Some people love to build mobile applications. Not me. I try, not like it. So if you do that exploration when you're starting, number one, you're getting like a very, very broad experience and a bunch of different topics that is going to help you well. Number two, you're going to identify the thing. And if you identify the thing, you are going to go and seize it. And you're going to go and harness that sort of like a motivation and become good at it. You're going to be the person that does that. Ask yourself, how is every single person who has a business out there? Like, nobody wakes up one day and says, you know what, I'm going to become a plumber today. No, it's just people who like to tinker with things. And they happen to become good at them, and they start charging for their services. Same thing. That would be my advice to you. I tell my kid, you got to try different things. He's doing Python. He's doing game development with Roblox. He's doing some JavaScript. He's doing multiple things, and we're trying to find what he really wants to do. That would be my advice to you. And you go from there. Yeah. What are some free hosting deployment tools I can use to build some machine learning projects end-to-end to showcase my skills? My recommendation is build them on your computer. And if you want to host them somewhere, you can deploy them anywhere, like in AWS, in cloud, or anything. The question you need to answer is, you want to host them. Why? Well, maybe because you want to interview for a job. It's very easy to just host them for a couple of days while you interview. And it's not going to cost you a lot of money. It's probably going to cost you more money trying to figure out what to do than what is the hosting is going to be. Like, for example, if I host the model in AWS right now, if I host the model and I put it in an instance that is not running unless you call it, the cost is going to be zero if nobody calls it. Zero, literally. I can have it there. If an interviewer wants to try the solution that I built, they will use it. But when they stop, it costs nothing. So build it for your computer first. Learn how to deploy it to a cloud. The cost, I promise, is not going to be a big deal. So don't worry about that too much. What else? Anuradha.
Yeah. So you were talking about OMSCS, right, Georgia?
Yeah.
How relevant do you think it is now that we have so many platforms and other resources for learning ML?
Well, I don't know, because I went in 2015, so it's 10 years. So if the program is exactly the same, if it is exactly the same, well, it will be still relevant, but it could be better. That's what I would say. But 10 years ago, it was amazing. And the main thing that it gave me was the opportunity to, this literally happened. I was taking classes during the morning. I was working while I was taking classes. So I took a class during the morning, and literally 1 hour later, I would sit down at a meeting with a client, and I would be the person saying, we might be able to build a decision tree to solve this problem. And everyone was looking at me like, this guy is freaking smart. I learned about decision trees that same morning. I was just, doing that. And that was amazing, because the client would say, oh, that's amazing. That's great. Yeah, let's try. And I immediately had an opportunity to practice in a real project the thing that I just learned. So I did very well in my program. I can tell you that. I ended up with a GPA of 4, basically top. It was fine for me. It was nice. But a big part of it was that I was able to just find ways to apply what I was learning directly into the projects. I do not know how the project has changed, obviously. I don't know if they are including more modern classes. I have no idea. I don't know. It was a very good program. I would do it again with my eyes closed, for sure. Yeah.
Should I be looking for some particular programs they are offering? Because I have applied, but I don't know if it is relevant now.
Should you be looking to a different program? Was that the question?
No, for some specific programs that they're offering that will help today. With this program.
I mean, they have a machine learning class, which is the fundamentals of machine learning, one of the best classes, the hottest classes of the whole program, taught by Charles Isbell and Michael Littman. That's the name of the professors. So look into that class and see when was the last time they built it. To be honest with you, even if it's the same class that I took 10 years ago, these are fundamentals of machine learning that you need anyway. So I don't think that class should change a lot. But what I would recommend is look if they have any classes that look more modern, like something related to large language models, maybe transformers. Maybe they have introduced additional classes. They had like a computer vision class that I took. I think that computer vision class should be modernized. We should not be teaching today the stuff that I learned 10 years ago, because computer vision has made a lot of improvements over time. So those are the things that I will be looking at just to understand if they have changed the program. Also, I know there are amazing forums out there. You should be reading those forums and see what people are saying about those classes.
Can you share some of the forums?
I do not know them, but if you Google OSMCS, I know that a lot of people talk about that. This is a very popular program. I am referring to the Georgia Tech Online Masters program. That's the name is
OMSCS.
CS.
I'll type it. Also, following up with Mark's question, I mean, you can find a passion and do it every day, but what if you like everything, whatever you work on.
Just something. This is like saying, what if I like every boy in my class? Well, there's somebody who's you're gonna like a little bit more, right? I mean, you can do a bunch of stuff. That doesn't mean that you have to specialize, by the way. And some people like to be specialists. Some people, like me, would prefer to be generalists. But at least find an umbrella, an area where you can specialize. Like if you ask me, what are you specialists right now? I would say, I'm the person who takes a model that somebody else built, and I know how to put it in production and how to get it to work. Basically, today's class, I'm that guy. I'm very good at that because over time, I've specialized myself into doing that, into coming up with solutions to get better results from a model, right? Combining humans, combining hardware, etc. You can find, it could be, I know people who are very, very good at computer vision, building computer vision models, people that are very, very good at building APIs, building websites. So it could be a big umbrella. It doesn't have to be just this tiny little thing. But yeah, if you do what you love, you're going to tend to do more of it, and you're going to become better at it. And if you don't love it, that's okay. You understand that people have to eat, and you cannot. Sometimes you cannot just eat doing what you like. That's fine. But if you love it, that's better. It's just an advantage. Yeah.
I have been in the industry for like 7 years now. I have worked on IoT, on infrastructure, DevOps, coding, developer, everything. And I think I have one common thing among them which I like, and because of if it's missing, I don't like that field anymore, is I have to have some problems to solve. If I don't get anything to learn on a daily basis, I'll just lose interest.
That's great. That's great. So that's what you like. You have to seek more of that, right? So you have to maximize your possibilities of being put in positions where you need to solve something, when it's not just repetitive stuff. By the way, I know people, I have a friend, literally one of my best friends, he loves the repetitive stuff. So he doesn't want to think too much. Just give me something, and I know this is sort of the recipe for me to solve it. And I'm going to go through it, and I'm going to do it well. And awesome. But other people prefer to just the challenge of solving something that hasn't been solved before, or they have to think through it. Sounds like you are in that position. Great. Just maximize that for sure.
Thank you.
What's up?
Hey, Santiago. Is there a session in particular among these sessions that I should really zoom into for fine-tuning models? Like, for instance, like Stable Diffusion. If I wanted to improve upon a current library, is there a session in particular I should?
I do not touch on fine-tuning specifically. So what I would recommend is just, if you want to fine-tune a specific model like Stable Diffusion, I would recommend just to find a blog that explains how to do it. I do not go into too many details about fine-tuning.
Okay, thank you.
Sure.
Yeah, can you? Yes, can you hear me?
I can, yeah.
Thank you. I really appreciate what you've been going through here, because I can identify with one of your slides called latency. And I've been calling O3 Research and GPT-5 using the responses endpoint, setting the background to true because I want to do the polling. But I'm noticing that I can be in queue for up to 45 minutes or longer. And sometimes I time out, I retry. I guess the question for you is this the norm? Is going into the responses, they put you in queue, I understand that. But is that the norm to wait that long? And if it's so, then do you recommend using the smaller non-reasoning models to do some of that work instead of calling these bigger models? Because 45 minutes, it's not like that always, but it's more than 50% of the cases where you're waiting and waiting just to get your,
Yeah, that's the trade-off. So obviously they cannot serve every request they're getting. Therefore, they create the queues. And that is, if you really want to use the model to solve that problem and you don't mind waiting the 45 minutes, then yeah, you just do it. If not, you're going to have to degrade your expectation. You're going to have to use less quality for faster speed. again, it's the trade-off. I don't know if 45 minutes is the norm. I honestly don't use the thinking models that much, so I wouldn't know. But yeah, it sounds like that's what they're doing in the background just to accommodate all of the traffic that's coming in. Yeah.
Okay, thank you.
What else? Mark, what's up?
I'm sketching out in the next weeks or so a basic idea based on your slides and what I learned on the theory. I will not do practice much. What I have in mind to do. And can you then do me the favor to tell me if it's possible to do that, what I have in mind on my little computer, and if I miss some vital part of the chain I have in mind and so on? Would that be okay for you?
Yeah, for sure.
Thank you.
Yeah, when you have it, you share it, and I'm happy to give you feedback there.
Perfect. Thank you.
What else? Dinesh.
Yeah. Hi. So in the over the training course, we talked about like how we use the tabular data and what if it's a structure like unstructured data, like some videos and some documents and some random stuff, some calendar invites, and then so that how does that training, those kind of stuff works?
So, well, it really depends on what specific question is, but there are models that know how to process unstructured data. Like, for example, images are unstructured data. The way you would process those images is one image is, let's assume it's a black and white image, is basically a matrix of pixels. So you could have, number of rows times number of columns, input values, and that's how you would process an image. Text, you can vectorize text. We talk about, like, for example, you can generate vectors with the text, and that's how you would process them. So it doesn't matter what the original format is. You can create a mathematical representation of that original format and train a model of that mathematical representation to find patterns and find predictions or whatnot. Yeah.
Okay. But so with the unstructured data, like there won't be like what do you call the structify, the balanced.
What balance?
Sorry, what do you call the structify? Structify, is that correct?
Stratified.
Yeah, stratified. Yeah.
Class imbalance.
Stratifications.
Yeah, stratification. Yeah.
So how you organize the data. So the stratification comes, let's say you have a data set of images, okay? So there are images. And you also have another category. Your data set have another feature that says the time of day where an image was taken, daytime, afternoon, or nighttime, something like that, okay? So now you have two columns. The first column is an image, which is unstructured. And the second column is that category, which is the time of day. You could create splits using stratification by saying, I want the same percentage of daytime images and nighttime images on my training data than I have on my test data. So that's where you would use the stratification part. If you only have images, then no, you wouldn't. Need
just out of curiosity, this is like so this OpenAI, like whatever you query, even the local school, the teacher's email address and all sort of things, it's able to capture. Just like how do they do, like what in the course, like you said, like we have to very careful about the data leakage and stuff like that. On an OpenAI scale, how do they manage to do all these things?
They don't. So that's the problem. So they don't.
Half of it.
So it's just so the way they train these models is a little bit different. So let me give you just one example of how they could train this. By the way, I don't know exactly how they do it.
Just out of curiosity, that's not.
So One way to train these models is, let's say you want to train with images. And the way you do it, you take a patch of an image and you remove it. And you ask the model to reproduce the patch that was there. And that's how you teach the model. It's a very different model than a classification model or technique. It's a technique where you remove a portion of the let's say a sentence. You have a whole paragraph, and I remove 3 words, and I ask the model, can you predict what those 3 words were? And that's how it's a self-supervised approach, which is different than a supervised approach or unsupervised approach. So there are multiple sort of like under machine learning, there are all of these techniques, group of techniques. Supervised will be like how you train like a neural network with showing it like example, ground truth, example, ground truth. Self-supervised is this. You just take a lot of data, remove a portion of it, and just get the model to predict that. There is leakage that happens here. There's all sort of things that happens here. One form of leakage is asking these models to solve problems that the model has already seen during training. That happens all the time. Or you're gonna see that when they call that they have these benchmarks, and sometimes the models are amazing at these benchmarks. They score very high, and then they have this big headline, model is able to score super high at the benchmark of solving these exercises. And somebody clever comes and changes the wording of an exercise and the model completely fails. So like, how is this possible? Well, it's possible because the benchmark leaked. The model was trained on the benchmark, so the model becomes really good at solving that type of problem, but it doesn't generalize. Change the thing, the model completely fails. Have you seen them? Even GPT-5 right now is not able to count letters. Like right now, it's just not good at it. You ask how many R's are in strawberry, and GPT-5 is like 6. Like what? So it's just not good at solving those problems. It's just mimicking. It's just parroting answers. So yeah, there's a lot of leakage there. There's a lot of stuff that happens there. Yeah.
Thank you.
Cool. Let me check the Q&A. There's nothing new. All right. What else? Anything else? No? Sam?
Hey, Santiago, got a quick question. It's not particularly tying to our direct conversation, but I'm following your postings. And a while back, when you first evaluated Cursor AI as actually an early adopter, you spoke very highly of it, and you still do. I'm just now recently you've evaluated Copilot, and it appears that you are very impressed. Now, yesterday, Cursor made an update in their kind of billing terms and how they're going to calculate the monthly costs for some of their subscription levels. So it's kind of inviting me also to try. So I'm a Cursor user, but now it's kind of inviting me to look around. And I know you're already at the forefront. You've tried many other tools that you've blogged about. Which tool do you feel balances, like you said, there's that triangle, right? You got the quality, you got the speed, you got the cost. In your opinion, for pragmatically, which tool would you think is reasonable as an agent? That could develop a companion in a sense.
So there is no best recommendation than showing you what I'm using right now, and here it is. It's just, and as you can see, I have 1, 2, 3, 4, 5 instances of Visual Studio Code open at the same time. Those are 5 different projects that I'm currently working on. It's just VS Code. That's the one that I'm using. I do use Augment. Augment is they've paid me to promote them, but you guys here, I'm telling you, you're not gonna give me anything if you use them or not. But I think they're really good for certain use cases, specifically use cases that if you have a very large code base, Augment has this functionality where they index the code base beforehand and that is like, this is a very small project. It wouldn't give me anything here, but they will be great at answering questions from a code base that's very, very large. So I use them a lot. I lost my page here. But in general, I'm using Copilot right now. I'm not using Cursor. Nothing against Cursor, nothing at all. I think they have a great product. I do believe their app completion is better than Copilot's. I do believe that. They are not that different now than Copilot, that they don't justify for me having a separate subscription just to Cursor. They do have a big downside compared to Visual Studio Code, and it's Visual Studio Code obviously iterates under IDE way faster than what Cursor does. Cursor is an AI tool. They have to wait for Visual Studio to do new things, and then they have to integrate those new things in Cursor because they are a fork of Visual Studio Code. So Visual Studio Code will always be ahead of them. So that's one thing. The second thing is sometimes, unfortunately, Cursor will break functionality that Visual Studio Code has working because that integration is not just merging. Sometimes they have to make changes. One example is the dev containers that I use very heavily. It was broken at some point in Cursor. Like I couldn't load my dev containers in Cursor. And that is like a no, I have to stop using this. So those things have happened in the past. And now I'm at a point where Copilot is so good that might not be at the level of Cursor, but it's good enough for me to not have to put up with a separate tool. So that's why I started using Copilot again. Hopefully that makes sense.
Sure, but in terms of billing, because that's always an unknown question here. I mean, you're obviously using it heavily. How did you find the costs?
For Copilot,
yes.
You mean? Oh, I subscribe to the Pro plus whatever they call it, and I pay a fixed amount. That's what I pay. So I don't even know how would that translate in terms of numbers to Cursor. At that level, I'm not price sensitive, so I don't pay a lot of attention to discuss a little bit more than this one here. I just pay for their top subscription, and that's it. So I wouldn't be able to tell you how they compare in terms of cost.
Oh, sure. I'm asking because I believe the Pro, for example, in the US is $20 US. But there is a lot of fine print in terms of the Sonnet models and how they throttle that, and there is a quota. So I'm just asking that as you're practically using the tool day to day, you haven't run into any wall or any max. Okay, perfect.
That means I'm also not doing heavy vibe coding, asking the models for too much. These models help me write my code. I'm not helping them write code for me. If that makes sense. So, yeah. So I don't consider myself a pro AI user from that point of view. I'm not vibe coding with these models. Yeah.
Got it. Thank you.
Sure. Paul, what's up?
Yeah, I'm just curious, Santiago, based on everything that you're seeing in the landscape, if you were to focus, maybe like if you were to go back to school, or if you were to heavily focus in any particular area, is there something that you think you would focus on at this, based on what you're seeing?
I would say how you can use these models to produce better software, better solutions for. So it all comes down to solving problems for companies. So if you really want to have a job, is what are these companies going to need in the future that I can provide for them, right? It comes down to that. And I believe that these large language models represent it. They are before and after, and they're going to be a very useful component as part of bigger solutions for companies. Not that these models are going to solve the problems of companies. They won't anytime soon. That magic idea that Sam Altman is selling, that's just bull crap. These models are great components that are going to be part of a big solution, right? This is like the combustion engine. You don't write a combustion engine. You still have to produce tires and the wheel and windshield and all of your components for a car, right? So if you think about this as a combustion engine that is going to solve transportation, focused on how can you use it effectively to solve other problems. So that entails from how do you build systems that use this as the heart, like agents, for example, is a good area that we're just starting to see a little bit of traction with. They're not reliable right now. They're not awesome right now. They're not the solution to every problem, but they are an area that will keep growing. How can you build agents? How can you take advantage of agents? How do you deploy these systems? There is a lot that is not related to AI that I think is also useful. These models cannot deploy solutions to AWS. They don't know how to. They can tell you. Somebody has to go and click the buttons. It's very hard to do that. These models don't know a lot how, or they cannot put a solution in a Docker container and deploy it to Docker Hub or deploy it to ECS in AWS. Somebody has to go and do that and understand why you're doing that. So all of that area of DevOps and MLOps is very useful and will continue to be so, be really useful going forward. So those are the areas that I might be biased, but those are the areas that people should focus on. Yeah. What else? Nothing else? So we cut until next week. All right, so next week we're going to have 2 more sessions, obviously, office hours. First, on Monday, we're going to focus on monitoring and data drift and how things change and how to deal with all of that change. And then on Thursday, we are going to close with agents and MCP and retraining and all of that fun stuff. So yeah. In the meantime, ask your questions in Discord. Have a great weekend, everyone, and I'll see you next week.
See you. Thank you.
Bye-bye,
Thanks.
guys.
That's amazing. Bye-bye.